Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring some of the rarest things ever discovered in the universe. Space is unimaginably large, yet some objects and events remain astonishingly uncommon. A few exist only for a brief stage in cosmic history. Others are so difficult to create that astronomers have found only a handful of examples. Some stars spend just moments of their enormous lifetimes in their rarest forms. Certain planets survive in places where worlds seem unlikely to exist at all. There are also particles that can cross immense distances before they interact with anything. Rarity in the universe is not always about being small or hidden. Sometimes it comes from an extraordinary chain of events that must happen in exactly the right way. Tonight, we'll explore what makes these cosmic exceptions so unusual. We'll also discover why finding even one of them can change what scientists understand about the universe. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften, let your breathing slow, and allow your mind to settle into stillness as we embark on this fascinating journey together. Let's begin. Only one known planet has ever produced intelligent life. Earth is the only world where we know matter has organized itself into beings capable of building technology and studying the cosmos. That does not mean intelligent life exists nowhere else. It means every confound example we possess comes from this single planet. Astronomers have discovered thousands of worlds beyond the solar system, including rocky planets and worlds orbiting within regions where liquid water could potentially exist. Yet none has produced a confirmed biological signal. The search becomes even harder when intelligence enters the picture. A technological civilization might reveal itself through artificial radio transmissions or unusual atmospheric chemicals produced by industry. Scientists call such clues technosignatures. Searchers have listened to nearby stars and examined distant planetary systems, but nothing has yet crossed the threshold into confirmed extraterrestrial technology. That leaves Earth in an extraordinary position. Across everything humanity has observed so far, one small world remains the only place known to have produced creatures capable of asking whether anyone else is out there. The rarest stars can outshine entire galaxies before vanishing forever. For most of its existence, even a massive star shines with remarkable stability. Then a very small number end their lives with an eruption so bright that the individual stellar death becomes more luminous than billions of ordinary stars around it. These events are called superluminous supernova. They can produce at least 10 times more visible light than a typical core-collapse supernova. For a short period, one explosion can dominate the galaxy containing it. The star itself does not survive in its original form. Its center collapses while its outer layers race into space. One possible engine behind the extraordinary brightness is a newborn magnetar. This is a rapidly spinning neutron star with an immense magnetic field. As the magnetar loses rotational energy, that energy can pour into the expanding debris and keep it shining far longer than a normal explosion. Astronomers have identified only a few hundred exceptional core collapse events of this general superluminous class, making every new detection a valuable glimpse of an unusually violent stellar ending. Some black holes may have formed before the first stars existed. These hypothetical objects are known as primordial black holes. Unlike ordinary black holes, they would not have begun with the collapse of dying stars. Instead, they could have formed from unusually dense patches of matter during the universe's earliest moments. Conditions then were completely unlike anything that exists today. Matter and radiation were packed together at extreme temperatures while the universe expanded rapidly. If one region became dense enough, gravity might have overwhelmed the expansion locally and crushed that region into a black hole. The resulting objects could have formed with an enormous range of masses, depending on the exact mechanism involved. None has been confirmed. Scientists continue searching because primordial black holes could help answer major questions about cosmology. Some models allow them to contribute to the mysterious dark matter that outweighs ordinary matter throughout galaxies. Discovering even one would be astonishing. It would mean nature found a way to manufacture black holes before stars had appeared to provide the usual route to their creation. Neutron-star collisions create much of the universe's gold and platinum. Gold can begin with two dead stars spiraling toward destruction. Neutron stars contain matter crushed to extraordinary densities. When two of them orbit each other, they gradually lose energy through gravitational waves until they finally collide. The merger throws neutron-rich material into space at tremendous speeds. Inside that debris, atomic nuclei can capture neutrons with extraordinary rapidity. This process builds some of the heaviest elements found in nature. The radioactive material then powers a rapidly changing glow called a kilonova. In 2017, astronomers witnessed one after detecting gravitational waves from the merger known as GW170817. Telescopes followed the fading light and found evidence consistent with the production of heavy nuclei through this rapid neutron capture process. The event provided direct observational support for neutron-star mergers as an important source of precious heavy elements. Other explosive environments may contribute as well. Still, some of the gold now resting quietly on Earth may owe its existence to collisions between stellar remnants that occurred long before our solar system formed. A few planets orbit the burned remains of dead stars. The first confirmed planets discovered beyond our solar system were not found around a normal star. They were found around a pulsar. A pulsar is the rapidly spinning remnant left when a massive star collapses and explodes. It packs more mass than the Sun can contain into a sphere only about the size of a city. Its rotating magnetic field produces beams of radiation that sweep across space with remarkable regularity. Tiny changes in that timing revealed planets orbiting the pulsar PSR B1257+12. Their existence was astonishing because the system had already passed through a stellar catastrophe. The original planets may have been destroyed during the supernova. If so, the worlds now present could represent a second generation assembled from debris around the neutron star. Another possibility is that some material survived and later reorganized. Either way, pulsar planets proved that planet formation is not restricted to calm young stars. Worlds can appear around stellar remains after an environment has undergone one of nature's most violent transformations. The universe contains enormous regions with almost no galaxies inside them. Maps of the cosmos reveal that galaxies do not fill space evenly. They gather along enormous structures that surround immense regions containing remarkably little visible matter. These underpopulated regions are called cosmic voids. Some stretch for hundreds of millions of light years. They are not perfectly empty. Faint galaxies and thin traces of matter can still exist inside them. What makes a void extraordinary is how little it contains compared with the crowded filaments around it. Gravity helped create this pattern. Slight differences in density existed in the early universe. Denser regions attracted more matter as cosmic history unfolded, while underdense regions lost material to their surroundings and became increasingly empty. The result is the vast structure astronomers observe today. Voids are scientifically valuable because their shapes preserve information about how the universe expanded. Future surveys can measure thousands of them with increasing precision. Something that appears to contain almost nothing can therefore become a powerful laboratory for understanding dark energy and the large-scale evolution of the cosmos. Some stars are so ancient they formed near the cosmic dawn. A few surviving stars were born when the universe contained almost none of the heavier elements common today. One remarkable example is SMSS J0313-6708. Its chemical composition contains extraordinarily little iron. That matters because elements such as iron had to be manufactured inside earlier generations of stars. A star with almost none can therefore preserve conditions from a much younger universe. Researchers estimate that this ancient object formed only a few 100 million years after the Big Bang. It still survives because it began with a sufficiently low mass to burn its nuclear fuel slowly. Its atmosphere acts almost like archaeological evidence. The pattern of carbon and other elements suggests that the gas from which it formed may have been enriched by one of the first stellar explosions. Those vanished early stars cannot be observed directly today, yet their chemical fingerprints remain inside survivors. Studying an ancient star can therefore reveal something about stars that lived and died more than 13 billion years ago. Rare galaxies appear to contain almost no visible dark matter. Dark matter is normally thought to provide the hidden gravitational framework around which galaxies form. That is why NGC 1052-DF2 caused such surprise when measurements suggested it contained far less dark matter than astronomers expected. Another diffuse galaxy in the same general environment showed a similarly puzzling shortage. These objects are extremely faint and spread their stars across large areas. Determining their masses requires measuring how stars or compact star clusters move inside them. The interpretation has generated debate because distance measurements and assumptions about the systems can strongly affect the result. For NGC 1052-DF4, deep observations revealed evidence that a neighboring galaxy is gravitationally stripping material away. Dark matter extends farther from a galaxy's center than most of its stars, so it can be removed first during such an encounter. That offers one possible explanation for how a galaxy could lose much of its invisible mass while still retaining a visible stellar core. These unusual systems turn dark matter itself into something astronomers can investigate by noticing where it seems to be missing. Certain cosmic explosions release more energy than our Sun ever will. Gamma ray bursts rank among the most powerful explosions known. They arrive as sudden flashes of extremely energetic radiation from distant regions of the universe. Some last less than a second. Others continue for many seconds before fading into an afterglow that telescopes can follow across several wavelengths. The longer variety is often associated with the collapse of massive stars. During the catastrophe, material falls toward a newly formed compact object, while narrow jets can blast outward at speeds close to that of light. If one jet points toward Earth, the event appears astonishingly bright. In only seconds, a powerful burst can release an amount of energy comparable to what the Sun radiates across its entire lifetime. This does not mean the explosion shines equally in every direction, because much of the output can be concentrated into narrow beams. The scale is still extraordinary. A star that existed for millions of years can reach its final moments and suddenly produce one of the brightest detectable events across the observable universe. Some of the rarest detected high-energy cosmic neutrinos cross galaxies almost untouched. Neutrinos interact with ordinary matter so reluctantly that enormous numbers can pass through planets without striking a single atom. High-energy cosmic neutrinos are particularly valuable because their extreme energies point toward violent astrophysical environments. They can travel directly from regions that visible light may struggle to escape. That makes them unusual cosmic messengers. The Ice Cube Neutrino Observatory searches for them using more than a cubic kilometer of Antarctic ice. Most neutrinos pass straight through the detector. Very occasionally, one interacts with matter near the buried sensors and produces charged particles whose faint light can be measured. Those rare detections can reveal where the incoming neutrino originated. IceCube has linked high-energy neutrino emission with active galaxies containing feeding supermassive black holes. Because neutrinos carry no electric charge, magnetic fields do not bend their paths as they bend charged cosmic rays. An energetic neutrino can therefore cross immense intergalactic distances while preserving a directional clue to the extreme event that launched it. Catching one is like intercepting a messenger designed to pass almost invisibly through the universe. Magnetars possess the strongest confirmed magnetic fields in the universe. A magnetar begins as the collapsed core of a massive star, but its magnetic field places it in an extreme class of its own. These neutron stars can possess fields thousands of times stronger than those of ordinary neutron stars. Their magnetic energy can twist the crust until the surface fractures. The resulting disturbance can release intense bursts of X-rays and gamma rays. One famous event came from SGR 1806-20 in 2004. Although the magnetar was tens of thousands of light-years away, its giant flare was powerful enough to affect Earth's upper atmosphere. Magnetars are also remarkably compact. Their stellar mass is packed inside an object roughly comparable in width to a city. Scientists proposed their existence before observations established them as a distinct population of neutron stars. Today, only a small number are confirmed, compared with the enormous number of ordinary stars in the Milky Way. Their combination of compactness and magnetic intensity makes them natural laboratories for physical conditions that cannot be reproduced on Earth. Only a handful of stars are known to contain strange, heavy elements. One of astronomy's most peculiar stellar spectra belongs to Przybylski's star. When astronomers separate its light into individual wavelengths, they find an extraordinary chemical pattern, unlike that of an ordinary star. Numerous rare elements appear unusually abundant in its atmosphere. Researchers have even reported spectral lines attributed to short-lived radioactive actinides. Those identifications are difficult and remain scientifically challenging because stellar spectra can become extremely crowded. The deeper mystery is how such substances could remain detectable in a star where some radioactive isotopes should decay away on much shorter timescales than the star's age. Chemically peculiar stars can concentrate particular elements through processes such as atomic diffusion. Radiation pushes some ions upward, while gravity pulls others deeper into the atmosphere. That can create surface compositions that bear little resemblance to the star as a whole. Przybylski's star pushes this effect to an extraordinary extreme. Its spectrum has encouraged explanations involving unusual nuclear processes and material deposited from outside. No single explanation has settled every detail, which is exactly why this rare star continues to attract attention. Thorn-Zitka objects may hide neutron stars inside swollen giants. Imagine a neutron star entering the extended atmosphere of a much larger companion and spiraling all the way toward its center. The proposed result is a Thorn-Zitka object. From the outside, it could resemble an ordinary red supergiant. Deep inside, however, the normal stellar core would be replaced by an incredibly dense neutron star. Physicists Kip Thorne and Anna Zitkau explored the idea decades ago. Such an object might form during the complicated evolution of a close binary system. Astronomers have searched for chemical clues because unusual nuclear reactions near the embedded neutron star could potentially enrich the outer atmosphere with distinctive elements. The red supergiant HV 2112 was once highlighted as a promising candidate because its spectrum showed intriguing abundance patterns. Confirmation has remained elusive. Recent simulations have even questioned whether a neutron star could remain stable inside the envelope for long enough to create a lasting object. It might instead accrete matter rapidly and collapse into a black hole. Thorne-Zitkow objects therefore occupy a fascinating boundary between predicted stellar physics and objects still awaiting decisive observational proof. Some hypervelocity stars are escaping the Milky Way completely. Most stars travel around the galaxy while remaining permanently trapped by its gravity. Hypervelocity stars break that rule. They move so quickly that some have enough speed to escape the Milky Way and continue into intergalactic space. One dramatic way to produce such a runaway begins near the supermassive black hole at the center of our galaxy. If a tightly bound stellar system passes dangerously close, a black hole can capture one member while gravitationally flinging another outward at extraordinary velocity. Hubble observations traced the motion of the star He 0437-5439 back toward the galactic center. It was traveling at roughly 1.5 million miles per hour when studied. The journey creates a strange, stellar destiny. Instead of spending its life orbiting among billions of neighbors, an ejected star can eventually leave the galaxy that formed it. Other mechanisms can also create extreme stellar speeds. Exploding companions and interactions within dense systems may launch additional runaways. These rare stars allow astronomers to study violent gravitational encounters by following the objects those encounters throw away. Blue stragglers appear mysteriously younger than their ancient stellar neighbors. Old star clusters should follow a predictable pattern. Their most massive stars exhaust their fuel first, leaving lower mass stars behind. Yet astronomers repeatedly find unusually blue and luminous stars sitting among populations that should be too old to contain them. These apparent rule breakers are blue stragglers. Their color makes them look younger than neighboring stars that formed at roughly the same time. The secret is not that they were born recently. Many have been rejuvenated. A star can gain fresh material from a binary companion, increasing its mass and changing its appearance. Stellar collisions can also create blue stragglers in crowded environments. Recent observations across dozens of globular clusters have strengthened the case that mass transfer within binary systems is an especially important route. That means an ancient star can effectively alter its evolutionary clock by acquiring additional fuel. Blue stragglers do not truly reverse time. Instead, they reveal how interactions between stars can disrupt the simple life story expected from isolated object. In an old cluster, their unexpected brightness records a hidden history of stellar relationships. A few stars may be powered partly by captured dark matter. No dark matter-powered star has been confirmed, but theoretical models allow an extraordinary possibility. In regions where dark matter is unusually concentrated, particles could become gravitationally captured inside a forming star. If those particles can annihilate with one another, their mass would be converted into energy and heat the surrounding gas. This idea gave rise to models known as dark stars. Despite the name, such an object could be extremely luminous. Its unusual power source might delay the normal onset of nuclear fusion and allow the star to grow to enormous mass while remaining relatively cool at its surface. Researchers have suggested that conditions in the early universe may have been particularly suitable because the first structures formed inside dense concentrations of dark matter. Some proposed dark stars could eventually collapse and provide seeds from which early supermassive black holes grow. The entire scenario depends on properties of dark matter that remain unknown. That makes the idea especially intriguing. Finding one would not merely reveal a new kind of star. It could expose how an invisible form of matter behaves at the particle level. Dwarf Rayet stars expose their blazing interiors before exploding. Most stars hide the products of nuclear fusion beneath enormous outer envelopes. Wolf-Rayet stars have lost much of that covering. Powerful stellar winds or interactions with a companion can strip away their hydrogen-rich outer material and reveal layers that were once buried deeper inside. Their spectra can therefore show strong signatures of helium or products associated with later nuclear burning. These stars are extremely hot and luminous. They also shed material at tremendous rates through winds traveling thousands of kilometers per second. Some Wolf-Rayet systems manufacture carbon-rich dust when winds from two massive stars collide. The James Webb Space Telescope has watched expanding dust shells around Wolf-Rayet 140. New shells form as the stars approach one another during their elongated orbit. For many Wolf-Rayet stars, the stripped condition represents a late stage before core collapse. Astronomers study them because their exposed layers offer an unusual opportunity to examine the internal evolution of massive stars before their lives end. Instead of seeing only a stellar surface, we can observe material that once belonged much deeper within the star. Yellow hypergiants occupy one of the briefest stages in stellar evolution. A yellow hypergiant is what can happen when an extremely massive evolved star enters a violently unstable phase of its life. These stars are exceptionally luminous and lose matter at enormous rates. Their rarity comes partly from the fact that only very massive stars can become them. It also comes from how rapidly this evolutionary stage can pass. Astronomers therefore have relatively few confirmed examples to examine. In recent years, one remarkable star has offered the chance to watch such a transition unfold. WHG 64 in the Large Magellanic Cloud had long been known as an extreme red supergiant. Observations showed that its spectrum changed dramatically as the object became hotter and entered a yellow hypergiant state. Researchers reported evidence that this transformation occurred over an astonishingly short interval by stellar standards. The exact future of such stars remains uncertain. They may continue shedding their outer layers before eventually undergoing core collapse. Catching one in transition is valuable because human astronomy usually sees stellar evolution as isolated snapshots rather than watching a giant star visibly change its evolutionary identity. Rare carbon stars cloak themselves in soot made from their atmospheres. A carbon star can manufacture the material that eventually hides it from view. These evolved stars contain more carbon than oxygen in their outer atmospheres. That chemical imbalance changes which molecules and dust grains can form as material escapes from the stellar surface. Carbon-rich compounds condense in the cooling outflow and create tiny solid particles. Over time, those grains can build a dusty envelope around the star. The effect can become so strong that visible light from the stellar surface is heavily obscured, while the surrounding dust glows brightly in infrared wavelengths. The dust does not stay there forever. Stellar winds carry it outward into interstellar space. That makes evolved carbon-rich stars important contributors to the raw material available for later generations of stars and planetary systems. Some grains formed around ancient stars have even survived inside primitive solar system material. Carbon stars, therefore, do something remarkable near the ends of their lives. They manufacture solid particles from elements forged and rearranged through stellar evolution, then release those particles into the galaxy, where the same material can participate in entirely new cosmic talon A structures. Some white dwarfs are slowly crystallizing into planet-sized cosmic diamonds. A white dwarf is the dense stellar core left behind after a sun-like star reaches the end of its active life. It no longer produces energy through ordinary nuclear fusion. Instead, it spends billions of years cooling. Deep inside, matter exists at densities far beyond anything familiar on Earth. As the temperature gradually falls, the carbon and oxygen nuclei can begin arranging themselves into an ordered solid structure. In other words, the interior crystallizes. Astronomers long predicted this transformation, but observations from the Gaia mission revealed a clear signature of crystallization across a large population of white dwarfs. The process also releases energy, which temporarily slows the star's cooling and affects estimates of its age. Calling these remnants diamonds is an appealing shorthand because many contain crystallized carbon. Their internal structure is not identical to a jewelry diamond. The scale is far more extraordinary. A stellar remnant roughly comparable to Earth in size can progressively solidify from the inside outward. Far in the future, our own Sun is expected to become a white dwarf and eventually undergo this same transformation. Pulsars can spin hundreds of times during a single second. Some collapsed stars rotate so quickly that their surfaces move at a significant fraction of light speed. The fastest confirmed example spins more than 700 times every second. Each rotation sweeps beams of radio energy across space from regions near the magnetic poles. When one beam repeatedly crosses Earth, telescopes detect an astonishingly regular pulse. This is why these objects became known as pulsars. Their timing can rival the stability of atomic clocks over long periods. The speed becomes even more remarkable when you remember what is spinning. A neutron star can contain more mass than the Sun inside a sphere only a few tens of kilometers across. Many rapid pulsars were accelerated by stealing matter from a companion star. Gas spiraling inward transferred angular momentum and gradually spun the neutron star faster. Astronomers call this recycling. Eventually, the companion may be stripped down or transformed while the pulsar remains turning at an extraordinary rate. Somewhere in the galaxy, an object heavier than the Sun can complete hundreds of full rotations before you finish saying its name. At least one pulsar system contains planets that probably formed after stellar catastrophe. The planets around PSR B12 57+12 forced astronomers to reconsider where worlds can exist. Their host is not a normal star. It is a rapidly rotating neutron star left behind after a massive stellar explosion. Any original planetary system would have faced intense radiation and a violent loss of stellar material. Yet several small worlds now orbit the remnant with remarkable regularity. One leading possibility is that they formed afterward from a disk of debris surrounding the newly created pulsar. Material thrown outward during the explosion or supplied by a former companion could have settled into orbit and assembled into planets. Another possibility is that surviving worlds were dramatically altered rather than created from scratch. Their exact history remains debated. What matters is that planet formation clearly found a route through an environment that seemed almost impossible. The discovery also carried historical importance because these were the first confirmed planets found beyond our solar system. Humanity's first proven alien worlds were not circling a sun-like star. They were circling the remains of one that had already died. Rotating radio transients flash briefly before disappearing for hours. Some neutron stars refuse to behave like dependable cosmic clocks. Rotating radio transients can remain undetectable through hundreds or thousands of rotations before suddenly producing a short burst of radio waves. Then they vanish again. Their flashes may last only milliseconds, while the gaps between detectable bursts can stretch for minutes or even hours. That makes them easy to miss and difficult to study. Astronomers recognize the class after searching old survey data for isolated radio bursts rather than the regular pulse trains expected from conventional pulsars. The objects are thought to be rotating neutron stars, but researchers still debate why their emission appears so sporadic. Some may produce radio beams continuously, while our instruments detect only rare, bright pulses. Others may genuinely switch their radio emission on and off. Their slow and irregular appearance opens a hidden population of stellar remnants that ordinary pulsar searches can overlook. A neutron star could therefore sit inside our own galaxy for ages, while revealing itself to Earth through nothing more than an occasional millisecond flash, separated by long stretches of apparent silence. A few neutron stars may contain entirely unfamiliar forms of matter. The center of a neutron star reaches densities so extreme that ordinary descriptions of matter begin to break down. Atomic nuclei cannot remain intact there. Deeper still, even matter made mostly from neutrons may transform into something stranger. Physicists have proposed interiors containing hyperons. These are heavy particles that include strange quarks. Other models allow condensates of exotic particles or phases where quarks are no longer confined inside individual protons and neutrons. Some regions may also behave as superfluids that flow with almost no internal resistance. At the same time, charged particles could form superconducting states with unusual magnetic behavior. Nobody can open a neutron star and inspect its center directly. Instead, astronomers infer the possibilities by measuring masses and radii. They also study cooling rates and gravitational waves from mergers. Each measurement rules out some descriptions while leaving others alive. The puzzle is fundamental because these stellar remnants compress more than a sun's worth of matter into conditions unavailable in laboratories. Their centers may therefore contain phases of nature that have existed for billions of years without ever appearing naturally on Earth. Strange stars could be built from particles, unlike ordinary atomic nuclei. There is an even more radical possibility than a neutron star with an exotic core. The entire object might be made largely from strange quark matter. Normal protons and neutrons contain up and down quarks. Under extreme pressure, some theories suggest matter containing strange quarks could become stable as well. If that state were energetically favored, a collapsed stellar remnant might convert much of itself into a dense mixture of freely interacting quarks. The hypothetical result is called a strange star. From a distance, it could resemble an ordinary neutron star. Its mass might be comparable, and its diameter could be similar. The differences would hide in the relationship between those properties and in how the object cools or responds to violent events. Astronomers have occasionally proposed strange stars to explain unusual compact objects, but none has been confirmed. The idea remains scientifically serious because the behavior of matter at enormous density is still uncertain. Finding one would reveal that familiar atomic matter is not the only stable way nature can pack large quantities of substance into a stellar-sized object. Quark nova remain a possible second explosion after certain supernovas. A dying massive star may not always finish exploding after its first catastrophic collapse. In one speculative scenario, the newly formed neutron star survives for a time before its interior undergoes another profound transformation. If the pressure becomes high enough, ordinary neutron-rich matter could convert into deconfined quark matter. That sudden transition might release enough energy to drive a second explosion. Researchers call the proposed event a quark nova. It would occur after the original supernova rather than replacing it. The delay could range widely depending on the model and the evolving remnant. Material from the first explosion would already be expanding outward when the second shock caught up with it. This interaction might create unusual light curves or chemical signatures that resemble exceptionally bright stellar explosions. No quark nova has been securely identified. The concept depends on uncertain physics at densities beyond direct experimental reach. Even so, it gives astronomers a testable idea. An unusually complicated explosion could be more than one catastrophe layered together. A star might collapse once, through gravity, and then erupt again because matter deep inside it changed its fundamental form. Some neutron stars suddenly spin faster for reasons still debated. pulsars are famous for gradually slowing as they lose rotational energy. Yet some abruptly do the opposite. Their measured rotation jumps forward in an event known as a glitch. The change can be tiny, but pulsar timing is so precise that astronomers notice immediately. Afterward, the star may spend days or months relaxing toward its previous behavior. The leading explanation involves the extraordinary interior of the neutron star. Beneath the rigid crust lies matter thought to include a neutron superfluid. Tiny vortices within that superfluid carry rotation. Some may become pinned to structures in the crust, while the outer star slowly loses speed. A growing mismatch develops between the two regions. Eventually, many vortices can shift at once and transfer angular momentum outward. The crust suddenly speeds up. That elegant picture explains several features of glitches, but not every observation fits neatly. Some stars recover unusually. Others show accompanying changes in radiation. Glitches therefore offer something remarkable. A change in timing measured from thousands of light years away can reveal how invisible matter moves beneath the surface of one of the densest objects in existence. Binary pulsars let astronomers test gravity under exceptionally extreme conditions. When two compact stars orbit each other, gravity becomes strong enough to expose effects too subtle for ordinary planetary systems. The famous Hulse-Taylor pulsar provided one of the earliest dramatic examples. Its radio pulses allowed astronomers to measure the orbit with extraordinary precision. Over time, the orbital period was found to shrink exactly as expected if the system were losing energy through gravitational waves. This happened decades before those waves were detected directly on Earth. An even more powerful laboratory appeared with the discovery of the double pulsar system. Both objects are neutron stars, and both can be tracked as they race around a shared center of mass. Relativity predicts several unusual effects in such systems. Orbits slowly rotate. Signals experience delays while passing through curved spacetime. The stars themselves can alter how quickly clocks appear to run. Measurements repeatedly agree with Einstein's theory to remarkable precision. These systems are valuable because they perform experiments that no laboratory could build. Nature places stellar masses into close orbits. Then pulsars provide timing signals precise enough for humanity to watch gravity reveal its most demanding behavior. One magnetar flare briefly altered Earth's upper atmosphere from across the galaxy. On December 27th in 2004, a distant stellar remnant released a flash so intense that its effects reached our planet. The source was the magnetar SARS 1806-20. A sudden rearrangement of its immense magnetic field produced a giant flare dominated by high-energy radiation. The initial pulse lasted only a fraction of a second, yet satellites around Earth recorded an extraordinary burst. Instruments designed for other purposes were overwhelmed. More astonishingly, the radiation disturbed electrically charged layers high in Earth's atmosphere, despite traveling across tens of thousands of light-years first. Magnetar giant flares are extremely rare. Only a handful have been observed in our galaxy and its immediate neighborhood. The event showed just how much energy can be stored in the magnetic field of a compact stellar remnant. Nothing physically traveled from the magnetar to Earth at dangerous speeds beyond the radiation itself. Even so, an event on the far side of the Milky Way was powerful enough to produce measurable changes above our heads. A dead star briefly touched Earth without coming remotely close to it. Neutron star mountains may rise less than a centimeter high. Calling them mountains sounds almost absurd until gravity is considered. A neutron star has such a powerful gravitational field that any substantial bump on its surface would be crushed almost flat. Its crust can still support slight irregularities where one region rises above another. Depending on the star and the strength of its crust, the maximum height may be measured in centimeters rather than kilometers. Yet even such a tiny deformation can matter enormously. The material involved is fantastically dense, so a microscopic-looking feature can contain an extraordinary amount of mass by terrestrial standards. If the mountain is not perfectly aligned with the rotation axis, the spinning star could generate continuous gravitational waves. Researchers are searching for exactly those signals. Detecting them would reveal how strong neutron star crusts really are and how matter behaves under immense pressure. The phrase mountain, therefore, changes meaning completely on these objects. On Earth, mountains rise because rock can support kilometers of relief. On a neutron star, gravity is so severe that a feature shorter than a finger may represent one of the largest permanent landscapes the surface can physically sustain. Intermediate mass black holes remain surprisingly difficult to find. Astronomers know of black holes formed from stars, and they know of supermassive monsters containing millions or billions of solar masses. Between those groups lies a strangely elusive population. Intermediate mass black holes should contain hundreds or thousands of times the Sun's mass. Finding secure examples would help explain how the earliest giant black holes grew so quickly. Yet these middleweights are difficult to confirm because many do not feed brightly enough to announce themselves. Dense star clusters are promising places to search. If a hidden black hole sits at the center, surrounding stars should move under its gravitational influence. Astronomers can also watch for unusually luminous X-ray sources or gravitational waves produced when compact objects merge. Several strong candidates have emerged, but establishing their masses beyond doubt can be challenging. Their scarcity may hold important information about how black holes form. Perhaps they arise through repeated mergers inside clusters. Perhaps some are relics of unusually massive early stars. The gap between ordinary and supermassive black holes remains one of astronomy's most intriguing missing chapters, because something must connect the two ends of the family. Wandering black holes may travel silently between the stars. A black hole does not need a companion star or glowing disk to exist. If an isolated stellar black hole moves through relatively empty space, it can become almost perfectly dark. Astronomers estimate that the Milky Way should contain many such remnants, because countless massive stars have already lived and died. Most would be extraordinarily difficult to detect. One promising method uses gravity rather than light. When an unseen compact object passes nearly in front of a distant background star, its gravitational field bends and magnifies that star's light. This phenomenon is called gravitational microlensing. A massive lens can also make the apparent position of the background star shift slightly across the sky. By measuring both effects over months, astronomers can estimate the mass of the invisible object. Several long-duration events have produced candidates for isolated black holes or heavy neutron stars. The technique allows scientists to find objects that emit practically nothing themselves. Somewhere between the visible stars, dark stellar remnants may be traveling alone around the galaxy. We notice them only when chance alignment turns the light of another star into a temporary gravitational beacon. Some black holes are being launched from their host galaxies. A supermassive black hole normally sits near the center of its galaxy. Under the right conditions, gravity can throw one away. The process may occur after two galaxies merge. Their central black holes can spiral together and eventually collide. Gravitational waves carry energy away from the merger. If those waves are emitted more strongly in one direction, the newly formed black hole recoils in the opposite direction. The kick can reach thousands of kilometers per second in extreme theoretical cases. That may be enough to shift the object far from the galactic center, or even eject it completely. Astronomers search for these runaways by looking for quasars that appear displaced from their host galaxies or move at unusual speeds. Several intriguing candidates exist, although proving that a black hole has truly been kicked out is difficult. The consequences would be extraordinary. A galaxy could lose the object that once dominated its nucleus. Meanwhile, the expelled black hole might carry a small entourage of stars and gas into intergalactic space. Even the largest objects in galaxies are not guaranteed to remain where they formed. Primordial black holes might be smaller than ordinary astronomical objects. A black hole does not have to weigh as much as a star. If primordial black holes formed from dense fluctuations in the early universe, some could have begun with far smaller masses. General relativity allows this because the defining feature of a black hole is not enormous total mass. It is sufficient mass compressed within a small enough region. A primordial black hole with asteroid-like mass could therefore possess an event horizon smaller than an atom, while still weighing billions of tons. Even lighter examples may have evaporated long ago through Hawking radiation. The possible range depends on exactly how conditions unfolded soon after the Big Bang. Searches have ruled out primordial black holes as the sole source of dark matter across many mass ranges, but certain windows remain under investigation. Scientists look for their gravitational effects and for radiation associated with evaporation or accretion. If small primordial black holes exist today, they would overturn the everyday idea that black holes must be colossal. Nature could hide immense mass inside objects whose gravitational boundaries are microscopically tiny, created before ordinary stars had any opportunity to collapse. A black hole can orbit another black hole for millions of years. Binary black holes do not necessarily collide soon after becoming a pair. Two massive stars can evolve within the same system and eventually leave black holes orbiting one another. Supermassive black holes can also become bound after their host galaxies merge. Once paired, the objects may spend enormous stretches of time slowly losing orbital energy. Their separation gradually decreases. When they become sufficiently close, gravitational wave emission takes over and drives an accelerating spiral toward merger. The final stage can last mere moments, even though the earlier dance persisted for millions or billions of years. No material surface ever touches because black holes have event horizons rather than solid exteriors. Instead, the geometry of space-time becomes increasingly dynamic until the horizons combine. The result is a single larger black hole that rings briefly as it settles into equilibrium. Gravitational wave observatories have detected many stellar mass mergers, allowing astronomers to reconstruct the final seconds of systems whose histories were unimaginably long. The detectable collision is therefore only the final heartbeat of a partnership that may have survived across a significant fraction of cosmic history. Rare tidal disruption events tear entire stars into glowing streams. A star that ventures too close to a massive black hole can be destroyed without ever crossing the event horizon intact. Gravity pulls more strongly on the side of the star nearest the black hole than on the far side. Eventually, this difference overwhelms the star's own gravity and tears it apart. Astronomers call the catastrophe a tidal disruption event. Roughly half the shredded material may escape, while the rest remains gravitationally bound. That returning debris stretches into long streams before colliding and forming an intensely hot flow around the black hole. The system can brighten dramatically in ultraviolet light and X-rays. In some cases, powerful jets also emerge. These events are valuable because they illuminate black holes that were previously dormant. A quiet galactic nucleus can suddenly become one of the brightest objects in its neighborhood after consuming a single unfortunate star. The flare then fades as the supply of debris dwindles. Astronomers effectively watch a black hole switch on for a temporary meal. Each event provides a rare opportunity to study extreme gravity by following the destruction of an individual star in real time. Some black holes feed so quickly they challenge accepted growth limits. Matter approaching a black hole becomes extremely hot and luminous. That radiation pushes outward on the surrounding gas, creating a natural limit to how quickly material should fall inward under steady conditions. This benchmark is known as the Eddington limit. Yet astronomers have found black holes that appear to consume matter at rates above it. These super-Eddington systems reveal that the textbook limit is not an absolute speed barrier. Thick accretion disks can trap radiation and carry some of its energy inward. Powerful winds may also remove excess material while allowing a substantial flow to continue toward the center. The question becomes especially important when astronomers observe enormous quasars in the young universe. Some black holes had already reached masses of billions of suns surprisingly soon after cosmic history began. Standard growth from small stellar remnants can struggle to produce such giants quickly enough. Episodes of unusually rapid feeding may help solve the problem. A black hole can therefore enter a phase where its appetite appears to exceed the rate that its own radiation should normally permit, offering one possible route to creating cosmic giants in record time. Nearly dormant black holes can reveal themselves by bending background starlight. Some black holes have no glowing companion and almost nothing nearby to consume. In visible light, they can be genuinely invisible. Their gravity still leaves a detectable signature. If such an object crosses nearly in front of a more distant star, space-time around the black hole acts like a lens. The background star temporarily becomes brighter because multiple bent paths send additional light toward Earth. Unlike ordinary eclipses, nothing needs to glow or block the star directly. The effect depends entirely on gravity. By monitoring dense fields of stars for years, surveys can find these rare microlensing events. The longest-lasting cases are especially interesting because a more massive lens produces a slower event. Extremely precise astrometry adds another clue by measuring how the background star's apparent position shifts during the alignment. Together, the measurements can expose an otherwise dark, compact object and estimate its mass. This method is remarkable because the black hole may never consume anything while astronomers are watching. It gives itself away simply by passing through the correct line of sight and changing the path taken by someone else's light. A few galaxies may contain two actively feeding central black holes. When galaxies collide, their stars largely pass one another without direct impact, but their central black holes begin a much slower encounter. Each black hole can retain surrounding gas as the two galactic cores draw together. If both are feeding at the same time, astronomers may observe a dual-active galactic nucleus. These systems are valuable snapshots of a merger before the black holes themselves become a tight binary. They can reveal two luminous sources inside a galaxy whose structure has already been distorted by interaction. Finding genuine pairs requires careful work because bright star formation or jets can mimic some signatures. High-resolution radio, X-ray, and infrared observations help separate the candidates. Eventually, dynamical friction should draw the central objects closer. What happens at very small separations connects directly to the creation of supermassive black hole mergers and low-frequency gravitational waves. Dual active nuclei therefore capture a remarkable intermediate stage. Two galaxies that once evolved independently have begun becoming one, yet for a limited period each still carries a feeding central black hole. The future galaxy temporarily possesses two energetic hearts. Black hole mergers briefly radiate more power than all visible stars. The most violent part of a black hole merger lasts only a fraction of a second. During that instant, an extraordinary amount of energy leaves the system as gravitational waves. These are ripples in space-time itself rather than ordinary light. When the first directly detected merger swept past Earth in 2015, the two black holes combined into one, while several suns' worth of mass energy disappeared from the final mass budget. That energy was carried away by gravitational radiation. At peak output, the event produced more power than the combined light of the visible stars in the observable universe. Yet human eyes would have seen nothing, because the energy was not primarily electromagnetic. By the time the waves reached Earth after traveling for more than 1 billion years, they changed the length of detector arms by less than the width of a proton. That tiny movement revealed an event of almost incomprehensible power. Black holes can therefore collide in complete darkness, while momentarily becoming the most energetic known engines in the cosmos through distortions of space and time alone. Fast radio bursts can release astonishing energy within milliseconds. A radio telescope can stare into space and suddenly receive a flash that is over almost as soon as it begins. Fast radio bursts last for only milliseconds, yet many originate in galaxies hundreds of millions or billions of light years away. To remain detectable across those distances, the source must release an extraordinary amount of radio energy in an extremely short interval. Their discovery created a major astronomical mystery because the first events appeared without warning and did not immediately repeat. Today, astronomers know that at least some are connected to highly magnetized neutron stars. A magnetar inside our own galaxy produced a powerful radio burst in 2020 that strongly linked these objects to the phenomenon. That does not necessarily mean every burst has the same origin. Different environments may create similar flashes. Their signals also pass through intergalactic material before reaching Earth. The resulting delay between radio frequencies lets researchers estimate how much ionized matter lies along the route. A millisecond burst can therefore do more than announce an extreme event. It can probe otherwise difficult-to-see material across enormous cosmic distances. Some repeating radio bursts follow mysterious cycles lasting many days. Not every fast radio burst source behaves randomly. A few repeaters seem to become active during recurring windows. One famous source, known as FRB 180916, J0158 plus 65 produces bursts during a cycle lasting roughly 16 days. For part of that interval, radio flashes are much more likely to appear. Then the source becomes comparatively inactive before the pattern returns. Another repeater has shown a much longer cycle measured in months. These rhythms provide clues about what surrounds the burst source. One possibility is orbital motion. A neutron star may travel around a companion and become visible only when geometry or surrounding gas allows its radio emission to escape. Another possibility involves slow changes in the orientation of a rotating compact object. Researchers continue testing competing explanations because periodic behavior dramatically narrows the range of possible models. The source cannot simply be exploding once and disappearing. Something survives and resets. That transforms the mystery. Instead of asking what single catastrophe created the burst, astronomers can ask what cosmic machine repeatedly places itself into exactly the right condition to flash across the universe again. Long gamma-ray bursts announce the deaths of unusually massive stars. A long gamma-ray burst can begin when the core of an enormous star collapses and fails to produce an ordinary explosion. The center forms a black hole, or possibly an extremely magnetized neutron star. Meanwhile, material continues falling inward and creates a rapidly rotating disk. Under suitable conditions, the central engine launches narrow jets that punch through the collapsing star at almost the speed of light. If one jet points toward Earth, satellites detect a burst of gamma radiation that can last from several seconds to many minutes. After the high-energy flash fades, astronomers often discover a broad-line type of stellar explosion beneath it. These associations helped establish the connection between long bursts and the deaths of stripped, massive stars. The event is directional. An identical collapse occurring with its jet pointed elsewhere might never be recognized from Earth as a gamma-ray burst. That makes the phenomenon rarer to us than the underlying explosions themselves. What we observe is therefore a special alignment with one of nature's most powerful stellar deaths, seen almost directly down the barrel of a relativistic jet. Short gamma-ray bursts often mark collisions between compact stellar remains. For years, astronomers suspected that brief gamma-ray bursts came from merging neutron stars, but decisive evidence arrived only when several different messengers reached Earth from the same event. In August of 2017, gravitational wave detectors registered 2 neutron stars spiraling together. Less than 2 seconds later, satellites detected a short gamma-ray burst from the same region of sky. Telescopes then found a new source of visible and infrared light in a distant galaxy. The sequence-linked compact object merges directly to at least some short bursts. Their brevity now makes sense. The final collision happens extraordinarily quickly. A central black hole or massive neutron star can form while a disk of debris drives jets outward. If a jet is favorably oriented, gamma radiation escapes toward us. The discovery connected several branches of astronomy in one event. Gravitational waves revealed the motion of the dense objects, while light exposed the aftermath. A flash, lasting less than a few seconds, therefore marked the ending of a binary system that had probably spent immense stretches of time gradually spiraling toward one final collision. Superluminous supernovas shine far brighter than ordinary exploding stars. Some stellar explosions refuse to fade at the brightness expected from familiar supernova physics. Superluminous supernovas can become tens of times brighter than typical examples and remain brilliant for extended periods. Producing that much visible light requires an additional source of energy beyond the mechanisms that power many ordinary stellar deaths. One leading explanation involves a newborn magnetar spinning extremely rapidly. As its rotation slows, energy from the compact remnant can heat the expanding ejector from within. Another route may involve the explosion crashing into dense shells of material that the star expelled shortly before death. The collision converts kinetic energy into radiation. Individual events show enough variety that more than one mechanism may operate. Their rarity makes them especially valuable at great distances because their immense luminosity allows telescopes to detect them across much of cosmic history. They also reveal that some massive stars undergo extraordinary changes shortly before collapse. A supernova is already the destruction of a star. A superluminous one requires nature to find a way of making that destruction dramatically brighter than the standard catastrophe. Pair instability supernovas may destroy giant stars without leaving remnants. A sufficiently massive stellar core can encounter a remarkable problem caused by its own temperature. High-energy photons normally help provide pressure that supports the star against gravity. At extreme temperatures, some of those photons can transform into electron and positron pairs. Energy that had been supporting the core is suddenly diverted into creating particles. Pressure drops, gravity wins temporarily, and the core contracts. The contraction drives temperatures even higher and can ignite oxygen explosively. For stars within the right mass range, the resulting thermonuclear runaway may release enough energy to tear the entire star apart. No neutron star is left behind. No black hole necessarily remains. The star can simply disperse itself into space. This predicted event is called a pair instability supernova. Researchers continue searching for unambiguous examples because several exceptionally bright explosions have shown suggestive features without settling the question completely. The mechanism is striking because the star is not primarily destroyed by a collapsing iron core. Instead, the physics of light itself undermines the pressure holding the star together and triggers an explosion powerful enough to erase the original object. Kilonovas forge heavy elements inside rapidly expanding radioactive debris. After two neutron stars collide, the debris does not simply cool and disappear. It becomes a rapidly changing nuclear laboratory. Matter, expelled from the merger, contains an extraordinary abundance of free neutrons. Atomic nuclei capture them faster than radioactive decay can keep up. This rapid neutron capture process builds extremely heavy nuclei that ordinary stellar fusion cannot easily produce. Many of the newborn isotopes are unstable. As they decay toward more stable forms, they release energy that heats the expanding debris. That radioactive heating creates the glow astronomers call a kilonova. The color can change as different elements dominate the opacity of the ejector. Material containing lanthanides blocks visible light efficiently and shifts much of the emission toward infrared wavelengths. Observations of the famous merger in 2017 showed this evolution unfolding over days. Kilonovas therefore allow astronomers to watch fresh, heavy elements announce their own creation through radioactive decay. Unlike a supernova powered mainly by the destruction of a large star, this transient records the aftermath of two compact remnants combining and manufacturing new atomic species as their debris races outward. Failed supernovas may form black holes without brilliant visible explosions. Astronomers usually expect the death of a massive star to announce itself with a spectacular supernova. Theory predicts that some stars may instead disappear with surprisingly little display. If the collapsing core forms a black hole and the outward shock cannot successfully eject the stellar envelope, much of the star can fall inward. The result is sometimes called a failed supernova. Searching for one requires an unusual strategy. Rather than looking for something new appearing in the sky, astronomers repeatedly photograph nearby galaxies and ask whether a known massive star has vanished. One celebrated candidate involved a red supergiant in galaxy NGC 6946. It briefly brightened, then faded dramatically until its visible emission became extremely weak. Researchers have debated whether the star truly collapsed into a black hole or became hidden behind newly formed dust. That uncertainty shows how difficult the search is. A successful detection would reveal a route to black hole formation, but avoids the brilliant explosion normally associated with massive stellar death. One of the universe's most dramatic transformations could happen through disappearance rather than spectacle. Calcium-rich explosions occur far from the galaxies that produced their stars. Some rare stellar transients appear in places where very few stars should be dying at all. Calcium-rich explosions often occur far outside the bright regions of their host galaxies. After they fade, their spectra show unusually strong emission from calcium compared with many familiar supernova types. The combination has puzzled astronomers for years. Whatever progenitor creates them must either travel a long distance before exploding or belong to an old stellar population spread through faint galactic outskirts. Proposed explanations include unusual thermonuclear explosions involving white dwarfs and destructive encounters between compact stellar remnants. No single model has yet explained every observed event. Their remote locations make the puzzle more intriguing because young, massive stars normally die close to the regions where they formed. Calcium-rich transients seem disconnected from those nurseries. They may also contribute disproportionately to the distribution of calcium outside galaxies because their ejecta are released directly into sparse surroundings rather than dense galactic disks. A relatively faint explosion on the edge of nowhere could therefore help seed intergalactic space with an element essential to rocky planets and living bones. Rare luminous red nova revealed two stars merging into one. Sometimes a stellar system does not end with an explosion that destroys both participants. Two ordinary stars can instead spiral together and merge. As their orbit tightens, one star may become engulfed in the atmosphere of the other. Friction removes orbital energy and drives the pair closer until their structures can no longer remain separate. The merger ejects gas and produces a transient that brightens dramatically before becoming strikingly red as the material cools. Astronomers call these events luminous red nova. One of the most famous examples involved V1309, Scorpii. Remarkably, observations taken before its eruption showed a contact binary whose orbital period was shrinking. The system then produced a red transient consistent with the stars combining. This gave astronomers the rare chance to recognize a merger both before and after it happened. Other luminous red nova have revealed expanding shells of molecules and dust around their remnants. These events show that stellar evolution is not always a story of solitary stars. Sometimes two suns spend their final shared orbit, becoming a single new object. Some galaxies stopped forming stars when the universe was still young. Astronomers have found distant galaxies that appear to have shut down star formation surprisingly early in cosmic history. This is difficult to explain because young galaxies should contain plentiful gas for making new stars. Instead, these systems became quiescent, while the universe was still only a fraction of its present age. Something had apparently removed their fuel or prevented it from cooling into new stellar nurseries. A rapidly feeding central black hole is one possible culprit, because powerful outflows can heat or expel enormous quantities of gas. Violent bursts of star formation may also consume available material faster than it can be replaced. The discovery of these early dormant galaxies has become especially important with powerful infrared telescopes that can examine their ancient starlight in greater detail. Their existence means galaxy evolution could move remarkably quickly. A system could assemble a large population of stars and then effectively switch off within a relatively short cosmic interval. Instead of seeing the early universe as a place where every galaxy was busily growing, astronomers are finding surprisingly mature systems that had already completed much of their stellar development. Ultra-diffuse galaxies are enormous, yet contain remarkably few visible stars. Some galaxies occupy an area comparable to the Milky Way while producing only a tiny fraction of its light. These ghostly systems are called ultra-diffuse galaxies. Their stars are spread so thinly that the galaxy can almost disappear against the background sky. At first, astronomers wondered whether they were failed versions of large galaxies that somehow lost the ability to build substantial stellar populations. The reality appears more complicated. Some contain abundant dark matter, while others have produced controversial evidence for surprisingly little of it. Their histories may include strong stellar feedback or unusual interactions inside crowded galaxy clusters. One possibility is that gas was removed before many stars could form. Another is that the galaxy began with unusually high rotation and became spread across a larger region. Their faintness makes them challenging to discover because ordinary surveys can overlook objects with such low surface brightness. Yet once recognized, they reveal an important lesson. A galaxy's physical size does not tell you how many stars it contains. Nature can build something vast enough to span tens of thousands of light years and still leave it almost transparent. Green pea galaxies produce new stars at extraordinary rates. They received their playful name because early survey images showed them as tiny green dots. Behind that appearance are compact galaxies undergoing furious episodes of star formation. Their unusual color comes largely from strongly glowing oxygen in clouds of gas heated by young stars. Although these galaxies are relatively small, they can produce new stars at a rate that seems wildly disproportionate to their size. That makes them useful nearby counterparts to intensely star-forming galaxies from the distant universe. Astronomers can study them in much greater detail than objects whose light has traveled for most of cosmic history. Some green P galaxies also allow significant amounts of energetic ultraviolet radiation to escape. This matters because similar radiation from early galaxies is thought to have transformed neutral hydrogen throughout the young cosmos during the era of reionization. By studying these peculiar little systems, researchers can investigate a process that reshaped the entire universe. Their memorable name hides serious astrophysics. A modest galaxy appearing as little more than a colored speck can become a laboratory for understanding how young stars once changed the state of matter across intergalactic space. Ring galaxies can form when another galaxy punches through their centers. One of the strangest galactic shapes can begin with an almost direct collision. If a smaller galaxy travels through the central region of a larger disk, gravity can send a disturbance spreading outward through the larger galaxy. Gas becomes compressed along the moving wave and begins producing new stars. The result can resemble an enormous luminous ring surrounding a comparatively empty-looking center. The Cartwheel Galaxy is a spectacular example. Its outer ring contains vigorous star formation triggered by an ancient encounter. The collision did not make billions of stars physically fly outward together like debris from an explosion. Instead, the disturbance moved through the existing galactic disk and altered where gas became dense enough to form stars. This distinction helps explain how a recognizable ring can continue expanding through a galaxy. Over time, the shape will change as the system evolves and gravitational disturbances fade. Ring galaxies are uncommon because the collision geometry must be unusually well aligned. Most galactic encounters produce distortions without creating such striking symmetry. Occasionally, however, one galaxy passes through another at just the right angle and leaves behind a structure spanning tens of thousands of light-years. Polar ring galaxies rotate in two nearly perpendicular directions. Most galaxies have a dominant plane where their stars and gas orbit the center. Polar ring galaxies add a second structure that travels almost at right angles to the first. From the correct viewpoint, the system can resemble one galaxy wrapped inside another. The central body may look relatively ordinary, while a vast ring of gas and stars circles over its poles. Astronomers think these configurations often arise when galaxies interact and one system captures material from another. Instead of settling into the main galactic disk, the stolen gas can remain on a dramatically tilted orbit and eventually form stars there. Because the polar material moves through a different orientation, its speed gives researchers a valuable way to investigate the galaxy's gravitational field in 3 dimensions. That can reveal how unseen mass is distributed around the system. The structure is also surprisingly durable. A well-established polar ring can survive for billions of years rather than immediately collapsing into the central plane. These galaxies preserve evidence of ancient encounters in their geometry. Their unusual appearance is essentially a record of matter arriving from a direction that ordinary galaxy formation never intended. Compact elliptical galaxies may be the stripped hearts of larger systems. A compact elliptical can contain billions of stars squeezed into a remarkably small region. One way to create such an object may be to take a much larger galaxy and remove most of its outer material. This can happen near a massive neighbor. Repeated gravitational encounters pull away loosely bound stars from the outskirts, while the dense central region survives. What remains is not necessarily a galaxy that was born tiny. It may be the exposed core of something once far larger. The famous galaxy M32 near Andromeda has long been studied as a nearby example of this compact class. Its stellar population and structure provide clues about whether stripping shaped its present form. Astronomers have also discovered compact ellipticals surrounded by streams of stars that strongly support this destructive pathway. The idea gives galactic archaeology a dramatic twist. Instead of reconstructing a lost object from fossils or debris on a planet, researchers can study a surviving galactic nucleus while its former outer stars disperse through space. A small, dense galaxy may therefore be the remaining center of a system that once extended across a much greater volume. Dark galaxies could contain gas and dark matter, but almost no stars. Astronomers use the term dark galaxy for a particularly elusive possibility. Such an object would possess enough matter to behave gravitationally like a galaxy, but would have produced very few visible stars. Dark matter could dominate its mass, while neutral hydrogen provides detectable gas. Without substantial starlight, however, the system would be extremely difficult to recognize. Radio telescopes can search for hydrogen through a characteristic wavelength emitted by the atoms. Several candidates have appeared over the years, although many turned out to be tidal debris or extremely faint conventional galaxies after closer examination. That uncertainty is important because a convincing dark galaxy would test theories of galaxy formation. Computer simulations predict that numerous small dark matter halos should exist, yet many contain no obvious stellar system. Some may simply have failed to gather enough gas. Others may have lost their material before star formation began. Finding an essentially starless galaxy would reveal a stage of cosmic construction that normally remains invisible. It would show that assembling a gravitational structure and lighting it with stars are separate achievements, and nature may sometimes accomplish only the first. Jellyfish galaxies trail streams of gas while crossing crowded galaxy clusters. A galaxy falling through a cluster can experience something that resembles an enormous cosmic headwind. The space between cluster galaxies is not empty. It contains hot, diffuse gas. As a galaxy races through that environment, pressure from the surrounding material can strip away its own gas and stretch it into long, trailing structures. This process is called Ram pressure stripping. Viewed through a telescope, the resulting galaxy can resemble a jellyfish with luminous tentacles extending behind it. Those tails are not merely inert debris. Compressed gas within them can form new stars outside the galaxy's main disk. Eventually, however, stripping removes the raw material needed for future star formation inside the galaxy itself. The same process that creates a spectacular appearance can therefore help shut the galaxy down. Jellyfish galaxies let astronomers watch environment transform a stellar system while the process is actively occurring. A galaxy enters a dense cluster carrying its own reservoir of gas. Motion through the cluster then peels that reservoir away. Over cosmic time, this can turn a once productive spiral into a much quieter member of the crowded galactic community. Relic galaxies have remained almost unchanged since the early universe. Most large galaxies have endured mergers and prolonged episodes of growth. A rare few appear to have escaped much of that later history. These objects are sometimes called relic galaxies because their compact structures and ancient stellar populations resemble massive galaxies seen at much greater distances. One remarkable example lies surprisingly close to the Milky Way by cosmic standards. NGC 1277 contains an unusually dense concentration of old stars and shows little evidence that it accumulated the broad outer envelope expected from repeated mergers. Its stars seem to have formed rapidly long ago before the system entered an extended period of relative isolation. That makes it valuable because astronomers normally study ancient galaxies by observing them across billions of light-years. A nearby relic offers a much clearer view of similar conditions. Individual details that would be impossible to resolve in a very distant object become accessible. Such galaxies are not frozen in a literal sense. Their stars continue to age and orbit. What remained unusually preserved is the overall architecture. Finding one is like discovering an early chapter of galaxy formation, but somehow avoided being heavily rewritten by everything that happened afterward. A few galaxies rotate without showing the expected influence of dark matter. Galaxy rotation normally provides some of the strongest evidence for invisible mass. Stars far from galactic centers often move too quickly to be held by visible matter alone. Yet a small number of unusual systems have been reported, where measured motions can be explained with much less dark matter than expected. These claims remain difficult because the answer depends on distance and the orientation of the galaxy. Gas motions can also be affected by interactions that complicate mass estimates. One intriguing example is AGC 1149-05. Studies of its rotating hydrogen disk have suggested that ordinary matter may account for most of the observed gravitational pull. Other researchers continue examining whether such systems genuinely lack dark matter, or whether measurement uncertainties can resolve the discrepancy. Either result would be informative. A securely confirmed galaxy with little dark matter would prove that visible and invisible matter can become dramatically separated during galaxy evolution. If improved observations restore a normal dark matter contribution, scientists learn how easily unusual geometry can mislead mass estimates. These rare galaxies are powerful precisely because they force astronomers to test one of modern cosmology's most familiar assumptions. Giant cosmic voids can span hundreds of millions of light years. Travel through one of the largest voids, and the universe would appear astonishingly sparse for an enormous distance. Galaxies do exist inside these regions, but they are far less numerous than average. The boundaries are where much of the missing matter is collected. Gravity gradually pulled material from underdense areas toward denser filaments as the universe evolved. This made voids larger and emptier over time. Some have diameters reaching hundreds of millions of light years. Their scale is difficult to grasp. Entire galaxy clusters could fit comfortably inside them while occupying only a small portion of the available volume. Voids also influence the motion of nearby galaxies, because matter tends to flow away from their interiors towards surrounding structures. Astronomers map them using immense redshift surveys that reconstruct where galaxies sit in 3 dimensions. These apparently vacant spaces carry cosmological information because their sizes and shapes respond to how structure grew and how cosmic expansion changed. A void is therefore not merely an absence. Its emptiness has a history. Matter once had opportunities to remain there, but gravity gradually concentrated much of it elsewhere and left behind a gigantic, underpopulated region. Enormous galaxy walls stretch farther than many people imagine possible. Galaxies assemble into structures far larger than individual clusters. Some lie along immense sheets and filaments that can extend across extraordinary distances. These arrangements are often described as galaxy walls. The Sloan Great War became famous when surveys revealed a connected concentration of galaxies stretching for more than 1 billion light-years by some definitions. Even larger proposed structures have since been reported, although determining where one structure ends and another begins can be statistically complicated. These walls do not behave like solid objects. They are patterns in the distribution of countless galaxies separated by enormous gaps. Their existence grows naturally from the cosmic web that developed from small density variations in the early universe. Dense regions attracted additional matter and gradually became filaments or sheets surrounding emptier voids. Researchers compare the largest claimed structures with cosmological simulations to determine whether their sizes are unusual within the standard model. The results require careful interpretation because enormous patterns can arise by chance inside an even larger universe. Still, galaxy walls demonstrate how far gravity can organize matter. The universe possesses architecture on scales so great that even entire galaxy clusters become merely small features within a much broader structure. Rare gravitational lenses create nearly perfect rings of distant light. When a massive galaxy lies almost exactly between Earth and a more distant source, gravity can transform the background object into a luminous circle. This is called an Einstein ring. The foreground galaxy bends space-time around itself. Light from the distant source therefore reaches Earth along several curved paths, instead of traveling straight toward us. If the alignment is exceptionally precise, those distorted images connect into a ring around the lensing galaxy. The effect does not mean the background object is physically ring-shaped. Its appearance has been reconstructed by gravity. Perfect or nearly perfect rings are uncommon because three objects must align with remarkable accuracy across enormous distances. Astronomers treasure them because the distortion provides a sensitive measurement of the mass in the foreground lens. That includes matter producing little or no light. The gravitational magnification can also reveal distant galaxies that would otherwise be too faint to study. An Einstein ring therefore performs two jobs simultaneously. It maps the gravity of one galaxy while enlarging another that lies much farther away. A rare accident of geometry becomes a natural telescope built entirely from curved spacetime. Some quasars appear several times because spacetime bends their light. A single quasar can reach Earth along more than one route. If a massive galaxy or galaxy cluster lies between us and the quasar, its gravity bends the incoming light into separate paths. Telescopes may then record 2 or 4 apparent quasars surrounding the foreground lens. These are not identical objects that form together. They are multiple images of the same distant source. The paths have different lengths and pass through slightly different regions of curved spacetime. As a result, light from a flare in the quasar can reach one image days or months before the same change appears in another. Astronomers measure these delays with great precision. Combined with a model of the foreground mass, they can use the delays to estimate cosmic distances and investigate the expansion rate of the universe. The technique turns an optical illusion into a measuring instrument. It also means that observers can effectively watch the same quasar at slightly different moments in its history within one telescope image. Gravity has created separate arrival schedules for photons that began their journeys in the same extraordinarily distant galactic nucleus. Cosmic strings remain hypothetical relics from the universe's earliest moments. Some theories of the early universe predict that enormous concentrations of energy could have become trapped along extraordinarily thin lines. These hypothetical objects are called cosmic strings. They should not be confused with the tiny fundamental strings proposed in certain theories of particle physics. A cosmic string would instead be a defect formed as the young universe cooled and changed state. Although incredibly narrow, one could contain a tremendous amount of energy per unit length and potentially extend across astronomical distances. Its gravity would behave unusually because space-time around the string would have a distinctive geometry. A background galaxy could appear doubled if the string passed between that galaxy and Earth. Oscillating loops might also produce characteristic gravitational waves. Astronomers have searched for both kinds of signature without finding conclusive evidence. That absence places limits on how common or energetic cosmic strings could be. Their appeal comes from what a detection would mean. A surviving string would be a physical relic from processes occurring at energies far beyond any human experiment. Instead of merely inferring the early universe from its aftermath, scientists could be observing a defect created during one of its first major transformations. Domain walls could be ancient boundaries between different vacuum states. Imagine the early universe undergoing a phase transition, while separate regions settle into different versions of the lowest energy state. Where those regions meet, theory allows a boundary called a domain wall to form. Such a wall would not be made from ordinary atoms. It would be a structure in underlying fields extending across space. Similar mathematical behavior appears in familiar physical systems when different regions choose different states during cooling. In cosmology, however, a stable domain wall could contain enormous energy and strongly influence the evolution of the universe. This creates a problem. If heavy walls were common and long-lived, their gravitational effects should be obvious today. The fact that we do not see such domination places powerful restrictions on models that produce them. Some theories allow walls to decay early or form with properties that make them much less disruptive. Scientists have proposed possible signatures involving gravitational waves or subtle cosmological effects. None has established their existence. Domain walls remain fascinating because they turn an abstract idea into something potentially physical. Different regions of space could once have chosen different vacuum configurations and briefly carried real boundaries between them. Primordial magnetic fields may have survived since before galaxies formed. Magnetic fields thread planets and stars today, but astronomers still debate where the universe's earliest magnetism came from. One possibility is that weak seed fields appeared before galaxies existed. Processes during cosmic phase transitions or other events in the young universe might have generated them. Later, collapsing gas and turbulent motion inside galaxies could have amplified those tiny beginnings into the much stronger fields observed now. Another possibility is that magnetism arose later through astrophysical processes associated with the first stars and galaxies. Distinguishing these histories is difficult because magnetic fields do not shine by themselves. Researchers instead study how they influence charged particles or alter the polarization of passing radiation. Gamma rays from distant sources can also provide indirect clues to weak magnetism in the vast spaces between galaxies. Evidence for truly primordial fields would be profound, because their present structure could retain information from epochs otherwise hidden from direct observation. A magnetic field measured across an almost empty region of space might therefore have an ancestry reaching back far beyond the first galaxies. Magnetism could be carrying a faint physical memory from the universe before familiar cosmic structures had formed. Dark matter clumps might exist without any stars or gas. Dark matter does not need to shine in order to gather under gravity. Cosmological simulations predict that galaxies should be surrounded by numerous smaller dark matter concentrations called subhalos. Some become homes for dwarf galaxies after ordinary gas settles inside them and forms stars. Others may remain completely dark because they are too small to capture or retain enough gas. Such starless clumps would be almost impossible to photograph directly. Astronomers must search for their gravitational effects instead. A dark subhalo passing near a stream of stars can disturb the stream and leave a gap or kink. Similar invisible structures can alter the appearance of strongly lensed background objects. These subtle signatures allow researchers to test how lumpy dark matter really is on small scales. The results could distinguish between different ideas about the particles making up this mysterious substance. If many starless subhalos are eventually detected, they would help solve a long-standing puzzle about why simulations predict more small structures than the number of visible satellite galaxies suggests. Entire gravitational structures may therefore surround the Milky Way, while containing nothing that an ordinary telescope could ever photograph. Cosmic neutrinos preserve information from places light cannot escape. Ordinary light can be absorbed or scattered by dense matter before it escapes an energetic cosmic environment. Neutrinos have a much easier journey. Because they interact so weakly, they can emerge from regions that are effectively opaque to photons and travel enormous distances with little disturbance. This makes them unique astronomical messengers. The Sun provides a nearby example. Neutrinos produced in nuclear reactions at its center escape almost immediately, while energy carried by photons can take an immensely longer route through repeated interactions before reaching the surface. In violent objects beyond the solar system, neutrinos can likewise carry information directly from deeply buried processes. The explosion of supernova 1987A produced a famous burst of detected neutrinos before the visible event reached its maximum brightness. Modern observatories now search for much higher energy examples from active galaxies and other extreme sources. The particles are extraordinarily difficult to detect, precisely because they pass through matter so readily. When one finally interacts inside a detector, however, it can carry evidence from a region that electromagnetic radiation could not reveal in the same direct way. The oldest possible gravitational waves may come from cosmic inflation. If inflation occurred, the universe underwent an extraordinary burst of expansion during an extremely early fraction of its existence. Quantum fluctuations present at that time could have produced gravitational waves with wavelengths later stretched to cosmic scales. These primordial waves would be far older than gravitational signals from colliding black holes, because they would originate before stars or galaxies existed. Nobody has detected them conclusively. Their most famous potential signature lies in the polarization pattern of the cosmic microwave background. A specific swirling pattern called B-mode polarization could preserve evidence of primordial gravitational waves. The search is difficult because dust within our own galaxy can produce polarization that mimics the desired signal. Experiments therefore observe multiple frequencies and compare large regions of sky to separate foreground contamination from cosmological effects. Other detectors are searching for primordial gravitational backgrounds at very different frequencies. A confirmed detection would open an observational window onto a period inaccessible to ordinary telescopes. Light cannot show us inflation directly. Gravitational waves might. They could preserve physical information from an era so early, but the familiar particles and structures of the later universe had not yet taken their recognizable forms. Free-floating planets travel through darkness without orbiting any star. Not every planet has a sunrise. Some worlds wander through interstellar space without being gravitationally bound to any star at all. Astronomers call them rogue or free-floating planets. They may begin inside ordinary planetary systems and later be ejected when gravitational encounters destabilize their orbits. Others could possibly form more directly from collapsing clouds that never accumulate enough mass to ignite as stars. Finding these objects is difficult because they receive no nearby starlight to reflect. Gravitational microlensing provides one method. A rogue planet crossing in front of a distant star can briefly magnify that star's light, even though the planet itself remains unseen. Young examples can also glow faintly in infrared because they retain heat from their formation. Estimates of their abundance remain uncertain, but surveys suggest they may represent a substantial hidden population. Conditions on such a world would be unlike those on Earth. Its sky would contain distant stars but no dominant sun. Yet internal heat or a thick atmosphere could potentially keep some environments warmer than expected. Planetary existence does not necessarily require permanent membership in a solar system. Pulsar planets endure intense radiation from rapidly spinning stellar corpses. Orbiting a pulsar means existing beside one of the harshest compact objects a planet can encounter. A pulsar produces beams of radiation and a powerful wind of energetic particles driven by its rotating magnetic field. Any nearby planet is therefore exposed to conditions completely unlike those around a calm main sequence star. The known pulsar system PSR B1257+12 contains several small planets whose precise gravitational influence can be detected through tiny changes in pulse arrival times. Their skies would receive no familiar steady sunlight from the neutron star. Instead, the environment would be dominated by high-energy radiation and the pulsar's rotational output. Researchers have explored whether sufficiently massive atmospheres might shield hypothetical planets in less extreme pulsar systems. But habitability remains highly speculative. The importance of these worlds lies elsewhere. They proved that planets can occupy environments astronomers once considered bizarre. A planetary system does not require a normal stellar host in order to remain gravitationally stable. Worlds can circle an object only kilometers across whose radio beam sweeps across the galaxy with extraordinary precision. Lava planets may possess oceans of molten rock and metal vapor. Place a rocky world close enough to its star, and the surface stops behaving anything like familiar geology. Some known exoplanets complete extremely tight orbits where stellar heating can raise daytime temperatures beyond the melting points of common rocks. Their surfaces may contain broad regions of molten silicate. Above those regions, vaporized rock can create a thin atmosphere containing substances such as sodium or silicon compounds, rather than ordinary water vapor. On a tidally locked world, one hemisphere may permanently face the star, while the opposite side remains much cooler. That enormous temperature difference could drive winds carrying vaporized material toward the night side. There, minerals might condense and return toward the surface before circulating again. Researchers model this as a kind of rock cycle, operating through evaporation rather than liquid water. Several ultra-hot rocky exoplanets are candidates for such environments. Observations of their thermal emission are beginning to test whether molten surfaces really exist. These planets take substances that form solid ground on Earth and place them into the role normally occupied by oceans and atmospheric gases. Familiar rock becomes weather. Carbon-rich planets could hide vast interiors filled with crystalline diamond. The chemistry available when a planet forms can profoundly alter what grows inside it. Earth developed in a region where oxygen was abundant enough for silicate rock to dominate. In a planetary system with a much higher carbon-to-oxygen ratio, different minerals could become important. Under immense internal pressure, carbon can adopt crystalline forms, including diamond. This inspired models of carbon-rich planets containing thick layers of diamond surrounding metallic or carbonric interiors. The popular phrase, "diamond planet," can be misleading because no astronomer has confirmed a world composed almost entirely of gemstone. Candidates once described that way remain uncertain because stellar chemistry and planetary composition are difficult to infer from afar. Even so, the underlying physics is real. Carbon subjected to suitable pressures can transform into diamond deep inside planets. Researchers also expect diamond formation within some giant ice planets through different chemical pathways. The possibility shows why exoplanet geology can differ radically from Earth's. Two rocky worlds with similar masses might possess entirely different interiors because their birth environment supplied different elemental ingredients. A planet's mineral structure can therefore record the chemistry of the disk from which it assembled. Chthonian planets may be exposed cores of vanished gas giants. A giant planet can migrate so close to its star that its enormous atmosphere begins to escape. Extreme radiation heats the upper layers and can drive gas away into space. If enough material is lost, the world may eventually resemble the dense core that once lay hidden beneath a much larger envelope. Astronomers sometimes call this hypothetical remnant a Chthonian planet. The name refers to the underworld in ancient Greek tradition, but the scientific idea concerns atmospheric destruction. Distinguishing an exposed giant planet core from an ordinary rocky planet is challenging because both could appear small and dense. Composition provides one clue. A stripped core might contain unusual proportions of heavy elements inherited from its former life inside a gas-rich planet. Researchers have identified several extremely hot exoplanets as possible examples, but the evolutionary histories remain uncertain. The concept matters because planets do not keep their original forms forever. Stellar radiation can sculpt them across billions of years. A world observed today as a compact rocky object might have begun as something resembling Neptune before losing layer after layer of atmosphere until only its deepest interior remained. Some planets orbit stars that survived swallowing their earlier companions. Astronomers have found planets around stars whose histories may include stellar mergers or engulfment events. These systems can be difficult to reconstruct because the dramatic interaction happened long before we began observing them. One route begins inside a multiple star system. As stars evolve, orbital changes can drive two of them together until one is swallowed by the other. A more distant planet may survive the disturbance and continue orbiting the merged star. In other scenarios, planets discovered around unusually massive evolved stars raise questions about whether the present host gained mass by consuming a companion. Chemical signatures and abnormal stellar rotation can preserve hints of such events. The situation shows how misleading a calm planetary system can be. A planet may appear to circle a single ordinary star today, while the star itself contains the combined material of two former suns. Surviving such a transformation would require the planet to remain far enough away to avoid destruction while its gravitational environment changed. These systems give astronomers a way to investigate the long-term stability of planets when stellar evolution becomes far more complicated than the solitary life of our Sun. Ultra-short period planets complete entire years within a single Earth day. Some planets orbit so close to their stars that sunrise to sunrise comparisons become almost meaningless. Ultra-short period planets finish a complete orbit in less than about one Earth day. Their stars dominate enormous portions of the sky from the planetary surface. Many of these worlds are rocky and several appear denser than Earth, which may reflect the loss of volatile material under relentless heating. The orbital speed is extraordinary because gravity is much stronger at such small distances. A year can pass between breakfast and bedtime on Earth. Researchers are fascinated by how planets reach these orbits because they probably did not all form exactly where we see them today. Gravitational interactions and tidal forces may gradually pull some worlds inward. Eventually, a planet can approach so close that the star begins distorting it. The strongest cases may be heading toward destruction as orbital energy dissipates. These systems let scientists study planetary survival at the very edge of what stable orbits permit. A world can remain recognizably planetary while traveling around its star hundreds of times during a single Earth year. Circumbinary planets experience skies ruled by two moving suns. Planets really do orbit pairs of stars. In a circumbinary system, the two stars circle one another while the planet travels around both of them on a wider path. Astronomers once wondered whether such complicated gravitational environments could support stable planets at all. Discoveries by the Kepler mission showed that they can. The geometry produces experiences impossible on Earth. From the planet, each sun would move relative to the other. Eclipses could alter the received starlight as one star passes in front of its partner. The changing stellar configuration also means astronomers cannot search for these planets using perfectly regular transits. Each crossing can occur at a slightly different time because the stars themselves are moving. That irregularity became one of the clues revealing the first systems. Planet formation around binary stars also tests theories because the young planetary disk must survive the gravitational influence of two central masses. Yet nature repeatedly manages it. The fictional image of a world beneath two suns turned out not to require fictional physics. Real planets can spend every year orbiting a constantly moving stellar partnership. Exomoons may be common, although none has been confirmed beyond doubt. Moons are everywhere in our own solar system, so astronomers expect many planets around other stars to possess them as well, proving that expectation has been surprisingly difficult. An exomoon is far smaller than its planet and usually produces only a subtle additional signal. One strategy looks for tiny changes in when a planet crosses its star. A massive moon can tug the planet around their shared center of mass and shift the transit timing. The moon might also produce its own smaller dip in starlight. Several candidates have attracted considerable attention, including possible moons around giant planets discovered by the Kepler mission. Follow-up studies have challenged or reinterpreted many of those signals. As a result, no exomoon currently enjoys the overwhelming confirmation achieved for thousands of exoplanets. Finding one would open an enormous new field. Large moons can influence planetary tides and axial stability. Some could even possess atmospheres or subsurface oceans of their own. Given how diverse moons are around nearby planets, the first secure detection beyond the solar system may reveal an object unlike anything astronomers originally expected to find. Trojan planets could share one orbit around the same star. Orbital mechanics allows two worlds to travel around a star at the same average distance without repeatedly colliding. The key is geometry. In a stable configuration, one planet can occupy a region roughly 60 degrees ahead of another along their shared orbit. A second stable region lies the same angle behind. These locations are associated with gravitational balance points known as Lagrange points. Our solar system already demonstrates the principle with swarms of Trojan asteroids sharing Jupiter's orbit. Extending the idea to two planet-sized bodies produces a fascinating possibility called co-orbital or Trojan planets. Simulations show that such arrangements can survive under suitable conditions. Astronomers have searched for evidence through transit timing and other orbital measurements. There have been intriguing candidates, but secure examples of two full-sized planets locked in a classic Trojan configuration remain elusive. Confirming one would broaden the meaning of a planetary orbit. We naturally imagine each planet occupying its own separate track around a star. Gravity allows something stranger. Two substantial worlds could keep the same year and follow the same orbital path while permanently remaining separated by a stable angular distance. Rogue moons may wander between stars after escaping their planetary systems. A moon normally seems inseparable from its planet, but gravitational chaos can break that relationship completely. During the violent early history of a planetary system, giant worlds can scatter one another into new orbits. Close encounters can also strip moons away from their hosts. The liberated moon might be captured elsewhere, crash into another object, or escape the entire system and enter interstellar space alone. Researchers sometimes call these objects nomadic moons or rogue exomoons. Detecting one would be exceptionally difficult because a small world without a nearby star reflects almost no light. Young examples could retain enough internal heat to glow faintly in infrared wavelengths. Others might carry thick atmospheres that slow the loss of warmth. A large moon could even preserve subsurface liquid through radioactive heating long after leaving its parent planet. None has been securely identified drifting independently between stars. Yet computer simulations show that planetary systems can eject enormous amounts of material. Somewhere in the darkness, objects that began life watching a giant planet fill their sky may now be traveling through the galaxy with no planet or sun beside them. A few asteroids travel through space from completely different star systems. For most of astronomical history, every small object seen passing through the solar system was assumed to belong here. That changed when Oumuamua was discovered in 2017. Its trajectory was unmistakably hyperbolic, which meant the sun could bend its path but could never hold it permanently. The object had arrived from interstellar space. Its brightness changed dramatically as it rotated, suggesting an unusually elongated or flattened shape. Astronomers also detected a slight acceleration that could not be explained by gravity alone, although no obvious cometary cloud was seen around it. Proposed explanations ranged from subtle outgassing to unusual surface properties. Whatever its exact nature, its origin beyond our system is clear. Since then, astronomers have become increasingly aware that material exchanged between planetary systems should be a normal consequence of planet formation. Giant planets can fling asteroids outward until they escape their home stars forever. Those fragments can then spend millions of years crossing the galaxy. Oumuamua showed that one can eventually pass close enough for humanity to notice, bringing physical material from another planetary system directly through our celestial neighborhood. Interstellar comets preserve material formed around distant, unknown suns. The discovery of Comet Borisov in 2019 gave astronomers something unprecedented. Unlike Oumuamua, this interstellar visitor clearly behaved like a comet. Sunlight warmed its surface and released gas and dust, producing a recognizable coma and tail. Its orbit showed that it had entered the solar system from beyond the sun's gravitational domain and would leave permanently. That meant astronomers could analyze matter that formed around another star without traveling anywhere. Spectroscopy revealed familiar cometary ingredients, but some chemical proportions differed from typical solar system comets. Borisov appeared unusually rich in carbon monoxide during part of its passage. That may hint at formation in a colder region around its original star or around a star with conditions different from those surrounding the young sun. The comet's home system is unknown because gravitational encounters over immense stretches of time make its path difficult to trace backward with certainty. Its importance lies in what survived the journey. Frozen material assembled around a distant star remained preserved during an interstellar crossing, then briefly warmed near our sun and released molecules that telescopes on Earth could examine. Active asteroids grow comet-like tails despite orbiting within the asteroid belt. The boundary between asteroid and comet turned out to be less tidy than astronomers once imagined. Some objects travel on ordinary asteroid-like orbits, yet suddenly develop tails or dusty clouds. These are known as active asteroids. Several different processes can produce the effect. A collision may blast surface material into space. Rapid rotation can weaken the object until dust slides or breaks away. Thermal cracking can also release particles after repeated heating. In other cases, buried ice may turn directly into gas and drag dust from the surface. Because identical appearances can arise through very different mechanisms, each active asteroid becomes a small detective story. Astronomers track how long the activity lasts and whether it returns at the same part of the orbit. Repeated activity near the Sun can point towards sublimating ice rather than a single impact. These objects matter because they reveal that the asteroid belt is not simply a collection of inert rocks. Small bodies continue to collide and fracture there today. Some even retain volatile material after billions of years. A tail does not automatically make an object a traditional comet. Sometimes an asteroid can temporarily imitate one. Centaurs behave partly like asteroids and partly like unstable comets. Between Jupiter and Neptune lives a population of small bodies whose futures are unusually uncertain. They are called centaurs because their behavior seems divided between two familiar categories. Their orbits resemble those of asteroids in some respects, yet many contain volatile material and can develop comet-like activity when sufficiently heated. More importantly, the giant planets constantly disturb their paths. A close encounter with Saturn or another massive world can dramatically alter a centaur's orbit. Over astronomical timescales, many are expected to be thrown outward, sent inward toward the Sun, or ejected from the solar system entirely. Some may eventually become short-period comets. The best-known example is Charon. It was initially classified as an asteroid before astronomers detected a surrounding coma, revealing active material escaping from its surface. Other centaurs possess rings or unexpected color variations that add to the diversity of the group. Their unstable location makes them temporary residents of the region they occupy. They are travelers caught between the distant reservoir of icy bodies and the warmer inner solar system. Watching them allows astronomers to study small worlds, while their orbits are actively being rewritten by giant planets. Contact binaries are two small worlds gently joined together. Some objects that look like single, oddly shaped bodies are actually two separate lobes touching at a narrow neck. This structure is called a contact binary. Arrokoth provided a spectacular example when the New Horizons spacecraft flew past it in 2019. The distant object consists of two flattened components joined together. Their remarkably undisturbed appearance suggests they did not smash into one another at high speed. Instead, the pieces may have formed nearby within the young solar system and gradually lost orbital energy until they came together slowly. That makes Arrokoth a valuable record of how planetesimals assembled. A violent collision would have shattered or heavily deformed the components. Their survival points toward a much gentler meeting. Similar double-lobed shapes appear among comets and asteroids, although not every example must share exactly the same history. Contact binaries challenge the instinct to imagine planetary formation as constant high-speed impact. At least some building blocks may have approached one another gradually enough to remain recognizable after joining. A world can therefore be assembled from two former companions, whose final orbital motion ended not with destruction, but with permanent contact. Metal-rich asteroids may be fragments of shattered planetary cores. When the young solar system was crowded with growing worlds, some small bodies became hot enough for their interiors to separate into layers. Dense iron and nickel sank toward their centers, while lighter rock moved upward. These differentiated objects were essentially miniature planets with metallic cores. Many were later destroyed by collisions. If a catastrophic impact stripped away the rocky exterior, pieces of the exposed core could survive as metal-rich asteroids. The asteroid Psyche has attracted enormous interest because radar observations and measurements of its density suggest that metal is an important part of its composition. Scientists once imagined it might be an almost completely exposed planetary core. More recent evidence points toward a complicated mixture of metal and rock, making its true history even more interesting. A spacecraft is traveling to investigate it directly. Studying such objects could reveal processes normally hidden thousands of kilometers beneath planetary surfaces. Earth's core is inaccessible to direct exploration, but a shattered protoplanet may have scattered comparable material into space. A metallic asteroid can therefore function as a surviving fragment from the internal anatomy of a world that ceased to exist billions of years ago. Minebelt comets contain ancient ice in unexpectedly warm regions. Ice is usually associated with the cold outer solar system, far beyond the orbit of Jupiter. Yet astronomers have found objects within the main asteroid belt that repeatedly release dust in a way consistent with buried ice turning into gas. These bodies are called main-belt comets. Their existence was surprising because they have spent immense periods much closer to the Sun than ordinary comets. Surface ice exposed for billions of years should disappear. The solution may lie underground. A protective layer of dust and rock can insulate ice and allow it to survive at depth. A small landslide or impact can expose a fresh patch, allowing sunlight to trigger temporary activity. These objects have important implications for the history of water in the inner solar system. Icy bodies from the asteroid region may have contributed some water to the young terrestrial planets during repeated impacts. Main belt comets also show that the early solar system did not divide cleanly into rocky material near the Sun and icy material farther away. Ancient volatile substances can survive in places where their presence was once considered unlikely, protected beneath dark surfaces for enormous stretches of time. Some comets become visible only once before leaving the Sun forever. Most familiar comets either return periodically or remain gravitationally bound on extremely long orbits. Hyperbolic comets follow a different destiny. If an object reaches the inner solar system with enough energy, its path around the Sun remains open rather than closing into an ellipse. After passing perihelion, it travels outward without returning. Some began inside our own system and gained escape velocity through a close encounter with a giant planet. Others can receive a smaller gravitational change after approaching the Sun on an orbit already close to the escape boundary. Interstellar visitors represent the most extreme examples because they were never bound to the Sun in the first place. For observers, this creates a unique encounter. Humanity may have only one opportunity to study the object before it disappears permanently into deep space. There will be no return apparition for future astronomers with better instruments. Measurements must be made during that brief passage. Every spectrum and image becomes irreplaceable. Comets are often described as recurring celestial visitors, but some are more accurately cosmic departures. We see them during the single moment when their paths cross the inner solar system before they continue outward without another scheduled meeting. Sedna follows an orbit so distant its origin remains uncertain. Sedna spends most of its extraordinary journey far beyond the familiar planets. Even at its closest approach, it remains roughly twice as far from the Sun as Neptune. At the distant end of its orbit, it travels hundreds of times farther from the Sun than Earth does. Completing one revolution takes more than 10,000 years. The real mystery is how Sedna acquired such an elongated path. Neptune is too distant from it to provide the necessary gravitational kick under present conditions. One possibility reaches back to the Sun's birth cluster. A neighboring star may have passed close enough to disturb Sedna, while the solar system was still young. Another explanation involves gravitational effects from an undiscovered distant planet. Sedna might also represent the inner edge of the Oort cloud, although its relationship to that enormous hypothetical reservoir remains uncertain. Only a small number of objects with somewhat similar extreme orbits are known. Each new discovery helps test the competing ideas. Sedna is not interesting merely because it travels far away. Its orbit appears to preserve evidence of an event or gravitational influence that astronomers have not yet conclusively identified. Antimatter is abundant in laboratories, but exceptionally scarce throughout ordinary space. Every known particle has an antimatter counterpart with the same mass but opposite electrical properties where charge applies. When matter and antimatter meet, they can annihilate and convert their mass into other forms of energy. Physicists routinely create antiparticles in accelerators, and positrons are also produced naturally in certain radioactive decays and energetic astrophysical processes. The deeper puzzle is why the observable universe is overwhelmingly built from matter. The early universe should have produced matter and antimatter in nearly equal amounts, according to simple expectations. If perfect balance had persisted, almost everything would have annihilated. Instead, a tiny excess of matter apparently survived and eventually formed galaxies, planets, and people. Experiments study subtle differences in the behavior of particles and antiparticles in search of an explanation. Large regions made from antimatter are considered unlikely because boundaries where they encountered normal matter should produce distinctive gamma radiation. None has been established. Antimatter itself is therefore not mythical or impossibly rare. We manufacture it. What remains astonishingly rare is antimatter assembled into enduring large-scale structures. The cosmos somehow chose matter overwhelmingly, and physicists still do not completely understand why. Strangelets could be tiny, stable fragments of hypothetical quark matter. Ordinary atomic nuclei are built from protons and neutrons. Each of those particles is itself made from quarks. At sufficiently extreme densities, theorists have explored whether quarks could exist together in larger collections without remaining confined inside individual nucleons. One proposed form is strange quark matter, which would contain up, down, and strange quarks. A small, stable fragment of this material is called a strangelet. No strangelet has been confirmed. Physicists have searched for them in cosmic rays and particle collisions, because discovering one would reveal an entirely new, stable form of matter. Theoretical predictions vary enormously. Strangelets might be unstable and disappear almost immediately, or certain combinations could persist under suitable conditions. Neutron-star collisions have been suggested as one possible natural source if strange matter exists inside compact stars. Safety concerns sometimes appear in popular discussions of strangelets, but collider experiments have not produced evidence of dangerous self-growing matter. Their real scientific importance is more fundamental. A confirmed strangelet would show that familiar nuclei are not the only possible long-lived arrangements of quarks. Nature may possess an additional category of matter that ordinary planets almost never encounter. Magnetic monopoles are predicted particles that nobody has conclusively detected. Cut an ordinary bar magnet in half, and each piece still has both a north and south pole. No matter how often the process is repeated, an isolated magnetic pole never appears. Some theories of particle physics predict that truly fundamental particles carrying a single magnetic charge could nevertheless exist. These hypothetical objects are called magnetic monopoles. Their discovery would be profound, because it could explain why electric charge occurs in discrete units and provide evidence for attempts to unify fundamental forces. Certain grand unified theories suggest monopoles may have formed during extremely early cosmic phase transitions. Inflation could then have diluted their abundance so dramatically that finding one today became extraordinarily unlikely. Experiments have searched through particle detector data and even examined unusual materials for trapped monopoles. There have been intriguing events, but no result has achieved convincing confirmation. A monopole would behave unlike any ordinary magnet because it could possess a north pole without a corresponding south pole, or the reverse. The concept is mathematically elegant enough that physicists have searched for decades. Nature has simply refused so far to reveal whether the particle exists outside the equations. Actions may be incredibly like particles filling the universe unseen. Dark matter outweighs the ordinary matter that forms stars and planets, yet its microscopic identity remains unknown. Actions are among the most intriguing candidates. They were originally proposed to solve an unrelated puzzle involving the strong nuclear force. Physicists then realized that enormous numbers of very light actions produced in the early universe could also behave as cold dark matter. An individual action might possess only a tiny fraction of an electron's mass, but the collective population could still exert the gravity required to shape galaxies. Detecting them is extremely difficult because their interactions with normal matter would be extraordinarily weak. Some experiments use intense magnetic fields and exquisitely sensitive electronics to search for the possibility that an action converts into a photon. Others look toward the sun, where action-like particles might potentially be produced in the hot interior. No experiment has confirmed them. The appeal of the idea lies in its efficiency. One hypothetical particle could connect a problem in nuclear physics with the astronomical mystery of invisible mass. If actions exist, the space around you could contain vast numbers of them, passing unnoticed through Earth at this very moment. Sterile neutrinos could exist without feeling most known forces. The three known types of neutrinos are already remarkably elusive. They ignore the electromagnetic force and interact through the weak nuclear force as well as gravity. A proposed sterile neutrino would go further. It would not participate directly in the weak force at all. Scientists could detect it only indirectly if it mixed with ordinary neutrinos or influenced other measurable processes. The idea emerged partly because neutrinos possess mass, which requires physics beyond the simplest original version of the Standard Model. Sterile neutrinos have also been proposed as possible contributors to dark matter, depending on their mass. Several experiments have reported anomalies that inspired interest in additional neutrino states, but results from different detectors have not produced a consistent discovery. Searchers continue using nuclear reactors, particle accelerators, and astronomical observations. The name sterile does not mean chemically inert. It describes the particle's extraordinary isolation from familiar interactions. If such neutrinos exist, entire populations could have crossed the universe while barely acknowledging ordinary matter. Discovering one would enlarge the known neutrino family and reveal a particle that lives even farther outside everyday physics than the already ghost-like neutrinos we know. Ultra-high-energy cosmic rays arrive with energies that remain difficult to explain. Every so often, Earth's atmosphere is struck by a subatomic particle carrying an almost ridiculous amount of energy. The most extreme cosmic rays can possess the kinetic energy of a well-hit tennis ball, concentrated into a single atomic nucleus or proton. When one enters the atmosphere, it collides with molecules and produces a vast cascade of secondary particles that spreads across kilometers. Ground-based observatories reconstruct the original event from this shower. The mystery is where such particles are accelerated. Ordinary stellar processes struggle to reach the required energies. Candidate sources include powerful jets from active galaxies and other environments containing enormous magnetic fields. Yet charged particles do not travel straight through space because galactic and intergalactic magnetism bends their trajectories. That makes tracing them back to their origins extremely difficult. The highest energy examples also interact with background radiation during long journeys, which limits how far they can travel before losing energy. Their very arrival therefore implies that sufficiently powerful accelerators exist somewhere within the accessible cosmic neighborhood. Nature is launching individual particles at energies human-made accelerators cannot remotely approach, and the exact machines responsible remain uncertain. Some atomic nuclei survive journeys across space at nearly light speed. Cosmic rays are not rays of light. Many are actual pieces of atoms stripped of their electrons and accelerated to enormous speeds. Protons dominate, but detectors also find nuclei ranging from helium to iron and beyond. These particles can spend immense periods traveling through magnetic fields before eventually colliding with Earth's atmosphere. A heavy nucleus moving close to light speed experiences conditions far removed from anything in an ordinary atom. Its electrons are gone, yet its protons and neutrons remain bound together, while the entire nucleus carries extraordinary kinetic energy. Where the different species originate is an active field of research. Supernova remnants can accelerate many lower-energy cosmic rays through shock waves. More energetic particles may require larger or more powerful environments. By measuring the proportions of different nuclei and their energies, researchers can infer something about their sources and what happened during the journey. Some unstable isotopes can even function as cosmic clocks because their decay constrains travel times. A fragment of an atomic nucleus can therefore cross interstellar space for ages before striking our atmosphere and revealing clues about remote astrophysical accelerators. Positronium forms briefly when matter binds directly with antimatter. An electron and its antimatter counterpart can do something remarkable before they destroy one another. Instead of annihilating immediately, the negatively charged electron can orbit together with the positively charged positron and form an exotic atom called positronium. No proton or neutron is required. The two particles have equal mass, so they orbit their shared center very differently from an electron moving around a heavy atomic nucleus. Positronium survives only briefly because its components eventually annihilate and produce photons. The exact lifetime depends on how their spins are arranged. Despite its fleeting existence, physicists can create positronium in laboratories and use it for extremely precise tests of quantum electrodynamics. Researchers have even produced excited forms and are investigating whether collections of positronium can be manipulated for more elaborate experiments. The system provides perhaps the cleanest possible meeting between matter and antimatter. They do not simply collide at random. For a tiny interval, they form a genuine bound structure with measurable energy levels. An atom can therefore exist without any conventional nucleus and contain equal amounts of matter and antimatter right up until the moment both disappear into radiation. Wollonium is an exotic atom built without any ordinary atomic nucleus. Replace the proton in hydrogen with a positively charged antimuon, and a strange but genuine atom appears. It is called muonium. An electron orbits the antimuon because the two particles carry opposite electric charges. Unlike an ordinary nucleus, the antimuon is considered an elementary particle rather than a composite object made from quarks. Muonium, therefore, gives physicists an exceptionally clean system for testing fundamental theories. It lasts only as long as its antimuon survives, which is a little over 2/millionths of a second on average. That tiny window is enough for precision experiments. Scientists measure its energy levels and magnetic behavior to compare them with predictions from quantum electrodynamics. Researchers are also searching for an astonishing transformation in which muonium could spontaneously become antimuonium. Observing that would violate familiar conservation rules and signal new physics. Despite its name, muonium contains no muon in the usual negative form. The positive antimuon takes the central role. For a few microseconds, nature constructs an atom with no proton or neutron at all, using an unstable elementary particle as the anchor around which an electron moves. Rydberg matter contains atoms expanded to extraordinary sizes by excited electrons. An ordinary atom is already mostly empty space, but a Rydberg atom pushes that idea to an extraordinary extreme. One electron is promoted into a state with very high energy. Its typical distance from the nucleus can then become hundreds or thousands of times greater than in the atom's normal condition. Collections of highly excited atoms can sometimes interact to form unusual condensed states described as Rydberg matter. Their exaggerated dimensions give them remarkable electrical properties and make neighboring atoms extraordinarily sensitive to one another. Even weak external fields can dramatically affect them. Physicists exploit these characteristics in experiments involving quantum information and precision sensing. Individual Rydberg atoms can be arranged with lasers and made to control whether nearby atoms become excited. This creates a phenomenon called Rydberg blockade that can act like a switch between quantum states. The atoms are not permanently enormous. Their excited configurations eventually decay and release energy. For the period in which they survive, however, the scale of the electronic orbit is transformed. Quantum mechanics can take a microscopic atom and temporarily expand one part of its structure toward dimensions that begin to approach the nanoscale world. Natural nuclear reactors once operated inside ancient uranium deposits on Earth. More than 1.5 billion years before humans built a reactor, nature assembled several of its own beneath what is now Gabon in Central Africa. The phenomenon was discovered at Oklo when scientists noticed that uranium ore contained slightly unusual isotope ratios. The explanation was extraordinary. Roughly 2 billion years ago, natural uranium contained a larger fraction of uranium-235 than it does today. In certain rich deposits, groundwater entered cracks in the ore and slowed neutrons enough to sustain nuclear fission. As the reaction heated the water, some boiled or moved away and reduced the neutron moderation. The reactor then weakened until water returned. This created a natural self-regulating cycle. The reactions continued intermittently over immense periods and produced many of the same kinds of fission products associated with engineered reactors. Their remains have helped scientists study how radioactive elements migrate through geological material across enormous spans of time. Oklo demonstrates that nuclear technology relies on physical conditions nature can occasionally assemble unaided. Long before any creature understood the atom, groundwater and uranium combined underground to create sustained nuclear chain reactions. Helium hydride was probably the universe's first molecular bond. Before stars existed, the young universe had to make chemistry from an extremely limited collection of ingredients. Hydrogen and helium dominated after the cosmos cooled enough for atomic nuclei to capture electrons. The first molecule expected to form was helium hydride ion. It consists of helium bonded with ionized hydrogen and is written by scientists as He H+. Chemists predicted its existence in space for decades, yet finding it proved surprisingly difficult. Laboratory experiments could make it, but astronomical searches repeatedly failed. Confirmation finally came from observations of the planetary nebula NGC 7027. Conditions there recreate some of the chemistry needed to produce the ion strongly enough for its distinctive infrared signal to become detectable. The discovery did more than identify an unusual molecule. It confirmed an important step in models describing the universe's first chemistry. Helium hydride could later react and help open pathways toward molecular hydrogen, which became crucial for cooling primordial gas before early stars formed. The first molecular bond in cosmic history was therefore likely created from two of the simplest elements available, long before planets provided anything resembling the chemical complexity surrounding us today. Technetium appears naturally only in tiny quantities and short-lived cosmic environments. Every isotope of technetium is radioactive. None survives indefinitely, which explains why substantial primordial deposits disappeared from Earth long ago. Yet technetium does exist naturally because ongoing nuclear processes can create fresh atoms. Tiny amounts arise from spontaneous fission in uranium ores. Far more dramatically, astronomers discovered technetium inside certain aging stars. That observation became a breakthrough in understanding how stars manufacture elements. If technetium appeared in a stellar atmosphere despite having no stable isotope, it must have been produced relatively recently on astronomical timescales. The star itself was therefore making heavy nuclei and transporting them toward its surface. This provided direct evidence for stellar nucleosynthesis while the process was still unfolding. Technetium can form through neutron capture reactions inside evolved giant stars before convective mixing brings newly created material outward. Its name comes from a word meaning artificial, because it was the first element produced artificially before being securely identified in nature. That history gives it an unusual identity. Humanity first knew it as something manufactured in a laboratory, then discovered that stars had been quietly producing the same unstable element for billions of years. Promethium is produced by stars but rarely survives for long. Between neodymium and samarium sits an element with no stable isotope at all. Promethium is radioactive in every form, and even its longest-lived isotopes decay on timescales tiny compared with the age of Earth. Any primordial promethium incorporated into our planet disappeared billions of years ago. The atoms present naturally today must therefore have been created more recently. Trace amounts can arise through the radioactive decay of heavier elements and through nuclear reactions. Stars can also manufacture promethium during neutron capture processes, although detecting it astronomically is challenging because its spectral signatures are faint and surrounding stellar atmospheres, contain many competing lines. Most promethium encountered in practical research is produced artificially in reactors. Its rarity once created a conspicuous gap in the periodic table. Chemists knew an element had to occupy the position, but struggled to isolate it convincingly until fission products provided enough material during the 20th century. Promethium illustrates how temporary an element can be on cosmic timescales. The laws of physics permit its nuclei to form, yet none possess the stability required to accumulate naturally over geological ages. Every promethium atom is effectively living on borrowed nuclear time. Astatine may be the rarest naturally occurring element in Earth's crust. At any given moment, the entire natural supply of astatine in Earth's crust may amount to less than a gram. Some estimates place it far below that. The reason is not that astatine cannot form. It appears briefly in radioactive decay chains involving much heavier elements. The problem is survival. Every known astatine isotope is unstable, and the longest-lived examples persist for only hours. An atom created naturally, therefore, disappears relatively quickly through further radioactive decay. New ones are continuously generated while older ones vanish, leaving an extraordinarily small standing population. Astatine lies beneath iodine on the periodic table and belongs to the halogen family, but its extreme scarcity makes its bulk chemical behavior difficult to study directly. Researchers usually create tiny quantities artificially and must work before the sample decays away. Nobody has ever assembled a visible lump of elemental astatine. Enough concentrated material would also heat itself through radioactivity, creating additional experimental problems. It occupies a strange position among the elements. Astatine is naturally produced on Earth right now, yet almost none exists at any single instant because nuclear instability erases it nearly as quickly as nature makes it. Super heavy elements exist for moments before their unstable nuclei break apart. At the far end of the periodic table, scientists create atoms that nature does not leave lying around for us to collect. Super heavy elements contain enormous numbers of protons packed into one nucleus. The electrical repulsion between those positively charged particles makes stability increasingly difficult. Researchers produce these atoms by accelerating one kind of nucleus into another and hoping that a rare collision causes them to fuse. Most attempts fail. Successful experiments may create only a few atoms after weeks or months of bombardment. The new nucleus then announces itself through a chain of radioactive decays. Some super-heavy isotopes survive for milliseconds, while others persist longer. Nuclear physicists are searching for an predicted region known as the island of stability, where particular combinations of protons and neutrons might produce unexpectedly longer lifetimes. Reaching it would test our understanding of how nuclei are structured. Elements this heavy also push chemistry into unusual territory because electrons move so rapidly near the highly charged nucleus that relativistic effects become important. At the edge of the periodic table, discovering an element can mean creating just a handful of atoms and watching how they disappear. Presolar grains contain minerals older than the solar system itself. Some meteorites contain microscopic pieces of solid matter that existed before the sun was born. These presolar grains survived the collapse of the cloud that formed our solar system and became trapped inside primitive asteroids. When pieces of those asteroids later reached Earth as meteorites, laboratories gained access to material originating around ancient stars. The grains can be made from substances such as silicon carbide and graphite. Their isotope ratios are dramatically different from typical solar system material, which reveals that they formed in other stellar environments. Some condensed in winds from aging giant stars. Others appear to have formed in supernova ejecta. Researchers isolate them through painstaking chemical procedures and examine individual grains using extremely sensitive instruments. Certain specimens have ages billions of years greater than the solar system itself. Holding a meteorite can therefore mean holding dust that already existed before Earth, the planets, or the Sun. These grains survived stellar outflows, interstellar travel, the birth of a new star system, and eventual incorporation into rock. Their tiny crystals are actual pieces of astrophysical history rather than merely light arriving from distant objects. Stardust crystals preserve chemical fingerprints from individual vanished stars. A microscopic grain can reveal what happened inside a star that no longer exists. Different nuclear reactions create distinctive proportions of isotopes. When dust condenses around an aging star or inside expanding supernova debris, those ratios become locked into the solid material. Billions of years later, scientists can measure them atom by atom inside presolar grains. The pattern may identify whether the parent star was a red giant, a nova, or a stellar explosion. Some grains contain isotopic combinations that expose specific neutron capture reactions occurring deep inside ancient stars. Others preserve evidence that material from different layers of a supernova mixed together before the dust crystallized. This makes stardust fundamentally different from most astronomical evidence. Telescopes analyze light from large populations or distant surfaces. A presolar crystal can provide a physical sample from one particular stellar environment. The original star may have disappeared before the solar system formed, but part of its chemical history survived in solid form. Scientists can place that grain into an instrument on Earth and reconstruct events that occurred inside an otherwise unreachable star. Cosmic archaeology sometimes operates on objects smaller than a grain of dust. The cosmic microwave background contains exceptionally rare patches of unusual temperature. Across most of the sky, the afterglow of the early universe is astonishingly uniform. Tiny temperature differences reveal the density fluctuations that eventually grew into galaxies. Against that regular pattern, a few unusually large features have attracted intense attention. The best known is the CMB cold spot. It covers a broad area of sky where the microwave background appears cooler than average in a statistically unusual way. Astronomers have investigated whether a vast, underdense region along the line of sight could account for part of the effect by subtly changing the energy of passing photons. Such structures do not seem to explain the entire anomaly straightforwardly. Another possibility is much less dramatic. In a universe containing countless random fluctuations, rare patterns occasionally appear simply by chance. More speculative explanations have also been proposed, but none is required by current evidence. The cold spot fascinates cosmologists precisely because unusual does not automatically mean new physics. Researchers must distinguish a genuine clue from an improbable but natural statistical accident. One strange patch in ancient radiation can therefore become a rigorous test of how confidently we understand the randomness built into our cosmological models. Intelligent observers may be among the rarest outcomes of cosmic evolution. The universe has spent billions of years producing stars and planets, yet we currently possess only one confirmed example of a species capable of investigating cosmic history. Whether that reflects genuine rarity or simply our limited search remains completely unknown. Life itself may begin readily once suitable chemistry exists, while technological intelligence could require a much more improbable sequence. Evolution on Earth offers no evidence that intelligence was an inevitable destination. Complex life persisted for immense periods without radio telescopes or spacecraft. Many successful organisms never developed technology because natural selection rewards survival rather than scientific capability. At the same time, one example cannot reveal the underlying probability. The Milky Way contains vast numbers of planets, and even an extremely unlikely process could happen repeatedly across such a large population. Searches for signals and other signs of technology are beginning to test that possibility. No confirmed extraterrestrial civilization has yet been found. This leaves humanity facing one of science's most extraordinary uncertainties. Intelligence capable of understanding the universe might be common enough to appear many times within a galaxy, or so rare that a world asking these questions is itself a cosmic exception. And that brings us to the end of our journey through some of the rarest things in the universe. We've encountered objects that exist only under extraordinary conditions. We've seen stars caught in brief stages of their lives, planets surviving in places that seem almost impossible, and particles that can cross vast distances while barely touching anything at all. Some of these rarities are the remains of violent events. Others are ancient survivors from the earliest chapters of cosmic history. And some may still exist only as possibilities, waiting for better telescopes or more sensitive instruments to reveal whether nature truly made them. What makes these discoveries so remarkable is not simply that they are uncommon. It is that each one shows us another way the universe can behave. And now, with all of that behind us, there is nothing more you need to follow. Let those distant stars continue without you for a while. Let the galaxies turn slowly in the darkness. The universe will keep moving long after this moment has passed. Allow your breathing to settle into its own rhythm. Let your shoulders soften against whatever is supporting you. There is nowhere else you need to be right now. If you enjoyed this journey, you're always welcome to like the video, subscribe to the channel, or leave a thought below. And if you happen to still be awake, there should be another sleepy science journey waiting for you on the screen. You can follow it whenever you're ready, and let the next subject carry your thoughts a little further. But for now, simply rest. Let the questions fade. Let the day grow distant, and allow yourself to drift naturally towards sleep. Sleep well, and good night.